Welcome to Multivariate Calculus for Machine Learning. In this course, we're going to cover a range of topics related to calculus that we think will be useful for you as you embark on your study of machine learning. We've tried to design this course so that you are able to rapidly develop an intuitive understanding of calculus and its applications. Where possible, we use graphics and animations to show what the maths is doing, so hopefully those of you who have bad memories of maths from high school will be left wondering why they ever found it confusing in the first place. However, those of you who are already quite competent with calculus will very likely be wondering why I've left out so much of the detail. Well, as I'm sure you can imagine, these two statements are related. We simply don't have time to cover all the details in this short course, and we also believe that they can sometimes put people off as they're quite overwhelming and stop people from pursuing the topic further. What we would like is for you to have learned enough about the language and applications of calculus that you'll feel confident to have a go at many of the wonderful machine learning courses already available online. But crucially, you'll know what to look up if you get stuck. Personally, although I'm using machine learning quite a lot in my job, this is not the core focus of my research. I'm not a developer of machine learning. So when designing this course, what I constantly had in mind was, what did I wish was available when I first started getting up to speed with machine learning? I hope that you find this course enjoyable, but most of all, that it gives you the confidence to dive into machine learning and see through the maths to the meaning. Welcome to Module 1 of 6 on this course introducing you to various concepts in calculus that we believe you'll find useful when studying machine learning. We start right from the basics but build you up fairly quickly to some interesting applications in Modules 5 and 6. This week we'll be focusing on the fundamental theory of calculus as well as some handy rules to speed things up. Where possible, I'm going to try and represent the concepts graphically so that you can see the derivations rather than just reading them. This sometimes means that we'll be skimming over a few details, but I'll also provide you with links to the more rigorous descriptions so that you can check them out if you're interested. Speaking for myself, I find it generally true that if I can't draw something, then I don't really get it, even if I could write down all the relevant equations. So, for the tests, I'm going to be asking you to identify solutions on graphs rather than grinding through the algebra for the most part. I hope you enjoy this first module, and I look forward to meeting many of you in the discussion forums. Before diving into calculus, we should first talk briefly about what functions are and where we use them. Essentially, a function is a relationship between some inputs and an output. So for example, if I had a function for modeling the distribution of temperature in this room, I might input the x, y, and z coordinates of a specific location I'm interested in, as well as the time t, and then the function would return me the temperature at that specific point in space at that moment in time. Like so many areas of maths, even if the idea is quite straightforward, often the notation can make things unnecessarily confusing. We'll be confronted by this again later in the course, and although it's sometimes fairly arbitrary historical reasons that decide this, like different people inventing different parts of maths at different times, it can also be because a particular notation style is more convenient for the specific application that it was developed for. However, and here is where a lot of the problems seem to arise, in order to use and play with the interesting applications of maths, it requires you to have done quite a large amount of often quite boring groundwork. Mathematical language is like learning any other language in that respect. You can't enjoy French poetry until you've learned a lot of French vocabulary and grammar, including all its quirks and irregularities. Quite understandably, some people find this off-putting. My French is still terrible, for example. This is made worse by the fact that most people have not even realised that there is maths poetry waiting for them at the end of this algebra tunnel. Machine learning is a whole genre of this poetry, so stick with us for the rest of the specialisation and you'll be ready to appreciate it and even write some of your own. Back to functions. We often see expressions such as f of x equals x squared plus 3. Perhaps the only thing worth mentioning about this notation style is, yes, I admit it, it is absurd that you should somehow just know that f brackets x means f is a function of x and not f multiplied by x. Sometimes this gets genuinely unclear when other bracket terms appear in your expression. For example, f of x equals this thing over here. You can assume that g, h, and a are all not variables, otherwise I would have to write f of x, g, h, and a. But you could only know for sure what was going on here if it was explained to you with more context. For example, is g a function being applied to x? What about h and a over here? Maybe they're both just constants, although you do face the same problem of missing context in any language, like the famous panda who goes to a restaurant and eats, shoots, and leaves, and they were both delicious. I can only apologise on behalf of maths and hopefully console you with two facts. Firstly, maths is at the core of my day job, and I often still get confused myself. And secondly, I still love it, and it gets better at second-guessing any missing context all the time, just like any other language. In the following exercise, I'm either going to show you some data or describe a concept to you, and you're going to have to select a function which you think might be used to represent it. This is not intended to be a difficult exercise, but what I would like you to understand is that selecting a function is the creative essence of science. This process of selecting a candidate function or hypothesis to model the world is what the great geniuses of science are remembered for. There then follows a potentially long and difficult process of testing this hypothesis, but there would be nothing to test without that first creative step. Calculus is simply the study of how these functions change with respect to their input variables, and it allows you to investigate and manipulate them. But ultimately, it's just a set of tools, and by the end of this course, you'll be using them yourself to model some real-world data. In the last video, I told you that calculus is just a set of tools for describing the relationship between a function and the change in its variables. And so in this video, we're going to explore what this means and how it might be useful. Let's start by having a look at a classic example, a speed versus time graph for a car. The most obvious thing this graph tells us is that the car's speed is not constant, because a constant speed would just be a flat, horizontal line. Furthermore, starting from zero speed at zero time, this car's speed is initially increasing with time, which is another way of saying that it is accelerating. Towards the end of the time period, the car's speed is shown to be rapidly decreasing, meaning that it is decelerating. There's a lot of information in this graph, and calculus will allow us to extract much more than just the speed. As we've already said, a horizontal line implies a constant speed, and then the more the line is sloping up, the greater the acceleration. In fact, acceleration can be defined as the local gradient of a speed-time graph. And clearly, acceleration itself is also a function of time in our example. We refer to the gradient at a single point as the local gradient, and we can illustrate this concept by drawing a tangent line, which is a straight line that touches the curve at a point and is also the same gradient of the curve at that point. After the initial acceleration, the car's speed reaches a peak and then begins to decelerate again. Deceleration has a negative slope. By recording the slope of these tangent lines at every point, we could plot an entirely new graph which would show us acceleration against time rather than speed against time. Before we plot this, for the complex case, let's think about what this acceleration time graph would look like for a car travelling at constant speed. Constant speed, we've got a flat horizontal line on our speed time graph. Then we can say that its gradient is, of course, 0. So the acceleration time graph would also just be a horizontal line, but in this case, at acceleration equals 0. Going back to our more complex case, let's just talk through what we should expect before we have a go at plotting it. So, initially, the gradient is positive and fairly constant, before it drops to 0 at the peak. It then becomes negative for a period before returning to 0. Let's now take a look at the graph for acceleration versus time overlaid onto the speed-time graph. Don't forget, the vertical axis for the blue line is speed and will have units of distance per time, whereas the vertical axis for the orange line is acceleration and will have units of distance per time squared. Because they've got different units, we could scale either of these two lines vertically in this plot, and the meaning would still be identical. However, these have been scaled just to make the most use of this plot area available. You can see that the points at which the acceleration function is 0, i.e. where it crosses the horizontal axis, coincide with where the speed time graph is flat and has 0 gradient, as we would expect. Although we will be discussing the formal definition of a derivative in a later video, what we've just done by eye is the essence of calculus, where we took a continuous function and described its slope at every point by constructing a new function, which is its derivative. We can, in principle, plot the derivative of the acceleration function following the same procedure, where we simply take the slope of the acceleration function at every point. This is the rate of change of acceleration, which we can also think of as being the second derivative of the speed, and it's actually referred to as the jerk of the car. Think of the jerky motion of a car as it stops and starts. Now, you may have never heard of this concept before, but hopefully, just by telling you that it's the derivative of the acceleration curve, this should be all you need to know to approximately sketch the jerk. Also very interesting is the idea of taking our baseline speed function and trying to imagine what function this would have been the gradient of, as in applying the inverse procedure to the one that we've just discussed. We can refer to this as the antiderivative, which, for those who've done calculus before, you may remember that it's closely related to something called the integral. For the example we're discussing here, it would represent the distance of the car from its starting position. This should make more sense when you consider that the change in the distance with respect to time, i.e. the slope of the distance time graph, i.e. how much distance you are covering per unit time, is just the speed. This analysis of slopes is all we're going to discuss in the video, and even though you haven't laid out yet the formal definition of calculus, you should already be able to answer lots of gradient type questions in the following exercise, which will put you in a very strong position to start thinking about differentiation more formally. Now that we've explored the relationship between functions and their gradient, we should be ready to lay out the more formal definition of a derivative. All we're going to do is translate the understanding about gradients that we saw in the previous video into some mathematical notation that we can write down. Unfortunately, this is the bit that a lot of people seem to find uncomfortable, so I will do my best to make it as painless as possible. We talked in the last video about horizontal lines having a gradient of 0, whilst upwards and downwards sloping lines having positive or negative gradients respectively. We can write down a definition of this concept by taking the example of a linear function which has the same gradient everywhere. So if we start by picking any 2 points, let's say here and here, we can then say that the gradient of this line is equal to the amount of that function that increases in this interval, divided by the length of the interval that we're considering. This description is often just condensed to the expression rise over run, where rise is the increase in the vertical direction and run is the distance along the horizontal axis. So, got the rise here and the run down here. If our function was sloping down and we picked points at the same horizontal locations, then our run would be the same, but our rise would now be negative. So our gradient equals rise divided by run. Fairly straightforward so far. But how does it relate to the more complicated functions we saw previously, where the gradient is different at every point? Now, the rise over run type gradient varies depending on where we choose our points. Let's pick a single point where we'd like to know the gradient, which we'll say is at point x on the horizontal axis. The value of our function at this point is therefore clearly just f of x. We're going to use the same logic as before, so we now need to pick a second point to draw our rise over run triangle. We can call the horizontal distance between our 2 points delta x, where, as usual, a delta is being used to express a small change in something, which means our second point must be at position x plus delta x. We can also write down the vertical position of our second point as a function f evaluated at our new location x plus delta x, i.e. f of x plus delta x. So we can now build an expression for the approximate gradient at our point x, based on the rise over run gradient between point x and any second point, remembering that the run will be our distance delta x and our rise is just the difference in heights of the 2 points. The last step in this process is simply to notice that for nice smooth continuous functions like the one we're showing here, as delta x gets smaller, the line connecting 2 points becomes a better and better approximation of the actual gradient at our point x. We can express this concept formally by using the limit notation scheme, which says that as delta x goes to 0, our expression will give us a function for our gradient at any point we choose, which we write as f dash of x or df by dx, depending on which notation scheme you prefer. This is a slightly strange concept as we're not talking about delta x equals 0, as dividing by 0 is not defined, but instead just when x is extremely close to 0. This process of extreme rise over run is what differentiation is. So when you're asked to differentiate a function, this literally just means substitute the function into this expression. We could fill up several videos with more robust interpretations of this infinitely small but non-zero delta x, but for now, just don't worry about it too much. We know more than enough to continue on our journey. Let's now put our new derivative expression into practice and see if it works. First, we should try this out on a linear function once again, as we know that the answer is just going to be a constant. So, what will the gradient of f of x equals 3x plus 2 be? So we can immediately sub this straight in and say, okay, f dash of x is going to equal the limit as delta x goes to 0 of, so we're taking our function and subbing it in, 3x plus delta x plus 2 minus 3x plus 2, all divided by delta x. Okay, and now we just work through the algebra. So we can say the limit of delta x goes to 0 of, and so we can expand these brackets out. So we're going to get 3x plus 3 delta x plus 2 minus 3x minus 2, all divided by delta x. Okay, and now we can look at this and say some of the terms are going to cancel. So this 3x here goes with this 3x here, and this plus 2 here goes with this minus 2 here. So we can keep going with this line and say, well, the limit, and it's going to be 3 delta x all over delta x. And then working down here, we can say, okay, well, the delta x's themselves are just going to cancel. So you end up with the limit of delta as delta x goes to 0 of just 3. Now this thing doesn't have a delta x in it. So actually, the answer for this one is just the number 3. Because all of the delta x terms have disappeared in this case, then the limit expression has no effect, so we can just ignore it. The gradient of our linear function is just a constant, as we expected. In fact, I'm sure many of you will have known already that the gradient of an equation of the form f equals ax plus b is just a. But it's reassuring to see this result emerging from our expression. Something else to take away from this simple example is that we actually differentiated two things at once, a 3x bit and a plus 2 bit. We could have differentiated them separately and then added them together and still got the same result. This interchangeability of the approach is called the sum rule, and it's pretty handy. Let's now try a slightly more complicated example. So, if we take the function f of x equals 5x squared, all we're going to do is take this thing and put it into our differentiation expression at the top. So, f dash of x equals the limit as delta x goes to 0 of, well, we've got 5x plus delta x all squared minus 5x squared, all divided by delta x. And all we're going to do now is work through the algebra and see what comes out the other side. So equals the limit, once again, as delta x goes to 0, of, and let's expand this thing out. So we're going to think x plus delta x squared, we're going to get x squared plus 2x delta x plus delta x squared. So which means we're going to get 5x squared plus 10x delta x plus 5 delta x squared. Once again, minus our 5x squared here. And all of that is divided by delta x. And now what have we got on this top row here? So we've got a pair of 5x squareds. So we can get rid of those because it's 5x squared and minus 5x squared over here. Okay, and we can also see that we've got a delta x in both the top terms and also in this bottom term here. So we can get rid of that with this and this over here. Okay, so let's write that line again. So we can now say it's the limit as delta x goes to 0 of, we've just got 10x plus 5 delta x. Okay, and we're looking at this thing. So it's saying the limit as delta x goes to 0 of this expression here. Now, only the second term has got a delta x in it. So what's going to happen? As our delta x goes to 0, we're going to just forget about this term. It's going to become extremely small. So we can write that this is equal to just 10x. So the derivative of the expression 5x squared is just 10x. We can generalize the lesson from this example to a rule for handling functions with powers of x. For example, if we take the function f of x equals ax to the power of b and substitute it into our differentiation expression, we will find that the derivative is always f dash of x equals abx to the power of b minus 1. So the original power gets multiplied to the front, and then the new power is just one less than it was before. This is known as the power rule, and you can put this into your calculus toolbox along with the sum rule that we saw earlier. So, you've now seen two examples in which we've applied the limit of rise over run method to differentiate two simple functions. But as you can probably imagine, if we wanted to differentiate a long, complicated expression, this process is going to become quite tedious. What we're going to see in later videos are more rules, like the sum rule and the power rule, which will help us speed up the process. However, before we do that, we're just going to look at some fairly magical special case functions which differentiate in an interesting way. In this video, we're going to run through three special case functions which give us interesting results when differentiated. The first example we're going to work through is the function f of x equals 1 over x, which you can see plotted in the corner. Now take a minute to notice that the gradient of this function is negative everywhere, except at the point x equals 0, where we can't see what it is. And actually, something quite interesting must be happening at this point, as on the negative side the function drops down, presumably towards negative infinity, but then it somehow re-emerges from above on the positive side. This sudden break in our otherwise smooth function is what we refer to as a discontinuity. We've mentioned already that the operation divide by 0 is undefined, which means that this function simply doesn't have a value at the point x equals 0. But what about the gradient? Well, let's sub our function into the differentiation expression to investigate. So if we take it f of x equals 1 over x, we can say that f dash of x must equal the limit as delta x goes to 0 of 1 over x plus delta x minus 1 over x, all divided by delta x. And we look at this thing and we say, well, we're going to have to make this top row, the numerator, have a single fraction. So we're going to have to combine these two fractions here, which means that we're going to have to make the denominators the same. So we'll multiply top and bottom by x here, and top and bottom by x plus delta x here. So we can say that the limit of x over x brackets x plus delta x minus x plus delta x over x brackets x plus delta x, all divided by, once again, delta x. Now looking at these two, we can see that we've got an x and a minus x, both with the same denominator. So we can subtract these now. So this cancels with this. So we can say, okay, this thing is going to be the limit of minus delta x divided by x brackets x plus delta x, all divided by delta x. Now at this point, you can see that you've got a delta x at the very top and a delta x at the bottom. So once again, these two terms cancel each other out. And what you're left with is the limit as delta x goes to 0 of minus 1 divided by x squared, we're going to open up this bracket, plus x delta x. And this, once again, is where the magic of limits comes into play. So we look at this function and we say, okay, this term here has got a delta x in it. This means that as delta x becomes very, very small, this term itself is going to become very small and therefore eventually become irrelevant. So what we can say is as we apply our limit, we can actually ignore this term here entirely. And we get minus 1 divided by x squared, which looks like this. So as we realize just by looking, this derivative function is negative everywhere. And like our base function, the derivative is also undefined at x equals 0. The second function we're going to look at, I'll start simply by explaining what it does. It's a function that has the special property that the value of the function, f of x, is always equal to the value of its own gradient, f dash of x. Now there is a boring function which has this property, which is the function f of x equals 0, because as it's a horizontal line, clearly both the function and the gradient are 0 everywhere. But there's also a much more interesting case. We're not going to work through the rigorous derivation, but we can skip through some of the more interesting bits. So let's start by noticing that our mystery function must always either be positive or always be negative, as if it ever tried to cross the horizontal axis, then both the function and the gradient would be 0, and so it would get stuck. So we'd just be at our boring function 0 again. The next thing to realize is that by virtue of always increasing or always decreasing, it can never return to the same value again. Plenty of functions could fit these criteria. And focusing on the positive case, they all look something like this. However, besides the 0 function, there is only one function that will satisfy all our demands. This is the exponential function, e to the x, where e is Euler's number, named after the 18th century mathematician. The number e, which is approximately 2.718, is very important for the study of calculus, but more than that, e, like pi, turns up all over mathematics and seems to be written all over the fabric of the universe. As differentiating e to the x gives us e to the x, clearly we can just keep differentiating this thing as many times as we'd like and nothing's going to change. This self-similarity is going to come in very handy. The last special case function that we're going to talk about in this video are the trigonometric functions, sine and cosine. You may recall that for a right-angled triangle, sine of angle x multiplied by the hypotenuse r gives you the length of the opposite side to the angle. And the graph of sine x looks like this. Let's take a look at this function and see if we can work out what shape its derivative would be by I. So, sine x starts with a positive gradient, which gently decreases until it's 0 at the top of the bump, and then it starts being negative again until it gets to the bottom of the next bump, and it turns out that the derivative of sine x is actually just cosine x. Now, what happens when we differentiate cosine x? Well, actually, we get minus sine x. Differentiating a third time gives us minus cosine x, and then, amazingly, differentiating a fourth time brings us all the way back to our original function, sine x. And then the pattern, of course, repeats. This self-similarity may remind you somewhat of the exponential function we discussed above, and that is because these trigonometric functions are actually just exponentials in disguise, albeit quite a convincing disguise, which we won't be discussing here. Many of the details of the functions that we've talked about in this video were skimmed over rather quickly, but for the benefit of this particular course, all I need you to understand is that differentiation is fundamentally quite a simple concept. Even when you might not be able to battle through all the algebra, you're ultimately still just looking for the rise over run gradient at each point. This pragmatic approach to calculus is going to come up again when we start talking about calculating gradients with computers. Sometimes we really can just find an equation for the gradient, as we've been doing for all of our examples so far. However, if instead of a nice smooth function, we just have discrete data points, then it can seem as if there's nothing for us to differentiate. But, as we shall see, rise over run comes back once again to save the day. Now that we've defined the differentiation operation in terms of an exact mathematical formula, it's become clear that even for relatively simple functions, calculating derivatives can be quite tedious. However, mathematicians have found a variety of convenient rules that allow us to avoid working through the limit of rise over run operation whenever possible. So far, we've met the sum rule and the power rule. In this video, we will cover a convenient shortcut for differentiating the product of two functions, which sensibly enough is called the product rule. It is of course possible to derive the product rule purely algebraically, but it doesn't really help you to develop much insight into what's going on. For all the topics covered in this course, I'd always prefer you came away with some degree of intuitive understanding rather than just watching me grind through examples. So, let's see if we can make any progress by drawing things. Imagine a rectangle where the length of one side is the function f of x and the other side is the function g of x. This means that the product of these two functions must give us the rectangle's area, which we can call a of x. Now consider that if we differentiate f of x times g of x, what we're really looking for is the change in area of our rectangle as we vary x. So let's see what happens to the area when we increase x by some small amount, delta x. A quick footnote here. For the case we've shown, we've picked a particularly friendly pair of functions where they both happen to increase with x. However, this won't necessarily always be the case, but it does just make drawing things a lot easier, and the conclusions would ultimately be the same. We can now divide up our rectangle into four regions, one of which was our original area, a of x. As the total edge length along the top is now f of x plus delta x, this means that the width of the new region must be the difference between the original width and the new width. And of course, the same logic applies to the height. We can now write an expression for just the extra area, which we will call delta A. This is the sum of the area of the three new rectangles. I want to avoid a drawn-out conversation about limits, but fundamentally, I hope you can see that as delta x goes to 0, although all of the new rectangles will shrink, it's the smallest rectangle that is going to shrink the fastest. This is the intuition that justifies how we can ultimately ignore the small rectangle and leave its contribution to the area out of our differential expression altogether. Now that we've got our expression for approximating delta x, we return to our original question. What is the derivative of a with respect to x? So we want the limit of delta a divided by x, i.e. rise over run, which means we also need to divide the right-hand side by delta x. We are so close at this point, all we need to do is slightly rearrange this equation. So firstly, by splitting it into two fractions, and then secondly, by moving f of x and g of x out of the numerators. What I hope you can see now is that the first part contains the definition of the derivative of g of x, and the second part contains the derivative of f of x. Which means that we are now ready to write down our final expression for the derivative of a with respect to x, which has now just been reduced to this. The derivative of a of x is just f of x times the derivative of g of x plus g of x times the derivative of f of x. So, we can now add the product rule to the list of tools in our calculus toolbox. If we want to differentiate the product of two functions, f of x and g of x, we simply find the sum of f of x, g dash of x, and g of x, f dash of x. This is going to come in really handy in later videos as we start to deal with some more complicated functions. See you then. So far, we have learned about the sum rule, the power rule, and the product rule. In this video, we will be discussing our fourth and final tool for this module, which is called the chain rule. Following this, our toolbox will then be sufficiently well stocked that we'll be ready to start tackling some heftier, more interesting problems. Sometimes we use functions as the inputs of other functions. As you can probably imagine, describing this can get a little bit confusing. So what we're going to do is give each of our functions meanings so that we can hopefully keep track of what's going on. Consider the nested function h of p of m. We have the function h, which is describing how happy I am, as a function of p, how many pizzas I've eaten that day. Then the pizzas I get to eat per day is itself a function of m, which is how much money I make. So we're still ultimately relating money to happiness, but via the concept of pizza. This nested function scenario comes up a lot in science and engineering as you relate chains of concepts together. And I suppose this particular example I've chosen here also gives you some insight into my priorities in life. So first I'm going to give you the function relating happiness and pizza, which has the following polynomial form. H of p equals minus a third p squared plus p plus 1 over 5, which is easily understandable from a plot. What we can see is that although without any pizza it's still possible to be happy in principle, my peak happiness is with about 1.5 pizzas. Any more pizza than this and I become less happy, and then beyond about 3 pizzas my happiness becomes rapidly negative. Next is our function relating pizza and money. P of m equals e to the power of m minus 1, which is also fairly straightforward to understand by looking at a plot. If you've got no money, you can't buy any pizza. But the more money you have, your pizza purchasing power increases exponentially. As at first you can take advantage of bulk buy discounts, but as you start getting really rich, you can buy your own pizza oven and eventually even build your own pizza factory. What we'd like to know is, by considering how much money I have now, how much effort should I put into making more if my aim is to be happy? To work this out, we're going to need to know what the rate of change of happiness is with respect to money, which is of course just dh by dm. For now, this relatively simple example, we could just directly substitute our pizza money function into our happiness pizza function, which would give us this, and then differentiate this thing directly. However, the chain rule provides us with a more elegant approach, which importantly will still work even for complicated functions where direct substitution like this may not be an option. Consider the derivative of h with respect to p and of p with respect to m. You'll notice that in this particular notation convention, where the derivatives are represented by quotients, the product of these two quantities looks like it would give you the desired function dh by dm. And in actual fact, this is a perfectly sensible way to think about what's going on. This approach is called the chain rule because in a sense we are making a chain of derivative relationships. Now this is certainly not what you might describe as a formal derivation, but it is already good enough to enable you to make use of the chain rule effectively. So, let's now apply this rule to our function. Firstly, let's differentiate our two functions, which give us dh by dp equals 1 minus 2 over 3p. dp by dm equals e to the power of m. And then multiplying these together is simple enough. However, we just need to remember that if we don't want pizza's p to appear in our final expression, then we just need to sub in our expression for p in terms of m. And then finally, by simply rearranging the terms, we recover the expression that we saw at the start of the video. So, dh by dm equals 1/3 e to the m times 5 minus 2 e to the power of m. And there we have it. Now don't forget that although for this simple example the chain rule didn't save us a huge amount of time compared to substituting in before the differentiation, don't let that fool you. What's magic about the chain rule is that for some real-world applications, we may not have a nice analytical expression for our function, but we may still have the derivatives. So being able to simply combine them with the chain rule becomes very powerful indeed. Before we finish, let's have a quick look at our money happiness function and its derivative on a graph. As we can see, if you're broke and it's really worthwhile making some money, but the benefit of getting more, especially once you have enough pizza, decreases dramatically and quickly becomes negative. We now have a fourth and final tool for the module, and in the next video we'll be putting them all to use in an example. In this video, we're going to work through a nasty looking function that will require us to use all 4 of the time-saving rules that we've learnt so far. To make matters worse, this function isn't going to describe anything familiar, so we'll just be flying blind and have to trust the maths. This will hopefully give you the confidence to dive into questions in the following exercise. Consider the rather nasty function f of x equals sine of 2x to the power of 5 plus 3x, all over e to the 7x. The essence of the sum, product, and chain rules are all about breaking your function down into manageable pieces. So the first thing to spot is that although it is currently expressed as a fraction, we can rewrite f of x as a product by moving the denominator up and raising it to the power of minus 1. There is actually another rule specifically for dealing with fractions directly, called the quotient rule, but it requires memorizing an extra expression, so we're not going to cover it in this course, as you can always use the approach that we've used here and rewrite your fraction as a product. Next, we'll split f of x up into the 2 parts of the product and work out how to differentiate each part separately, ready to apply the product rule later on. Let's start with the first part, which we can call g of x. We've got the trigonometric function sine applied to a polynomial 2x to the 5 plus 3x. This is a classic target for the chain rule. So, all we need to do is take our function and split it up into the 2 parts in order to apply the chain rule. So we can take g of u equals sine of u, and u of x equals 2x to the power of 5 plus 3x. Now we've got these 2 separate functions, and we're going to want to differentiate each of them in order to apply the chain rule. So we say, okay, g dash of u is going to just equal sine differentiates to cos, so cos u, and u dash of x is going to equal 10x to the power of 4 plus 3. Now we've got these 2 expressions, and I'm going to use a mixed notation for convenience. And I'm going to say, okay, well, dg by du multiplied by du by dx is going to give us, so we've got cos of u multiplied by 10x to the power of 4 plus 3. And now we're going to want to have a final expression that doesn't include a u. So we can think about these 2 cancelling each other out, and we get dg by dx. And this just equals, okay, cos of u, which is just 2x to the power of 5 plus 3x, multiplied by 10x to the power of 4 plus 3. And that's it. We now have an expression for the derivative of g of x, and already we've made use of the chain rule, the sum rule, and the power rule. Now for the second half of our original expression, which we will call h of x, once again we can simply apply the chain rule after splitting our function up. So we can say that h of v equals e to the v, and v of x equals minus 7x. Now once again, we've got our 2 functions, we just want to find the derivatives. So h prime of v is just going to equal, well, we've seen this one before, e to the v again. And v prime of x is going to just be minus 7. So combining these 2 back together and using different notation, we can say that dh by dv multiplied by dv by dx is just going to give us, we've got minus 7 times e to the minus 7x. And actually, already all of our v's have disappeared, so this is already our final expression. As we now have expressions for the derivatives of both parts of our product, we can just apply the product rule to generate the final answer. And that's it. We could rearrange and factorize this in various fancy ways, or even express it in terms of the original function. However, there is a saying amongst coders that I think can be applied quite generally, which is that premature optimization is the root of all evil, which in this case means don't spend time tidying things up and rearranging them until that you're sure that you've finished making a mess. I hope that you've managed to follow along with this example and will now have the confidence to apply our 4 rules to other problems yourself. In calculus, it's often the case that some initially scary-looking functions, like the one we worked with just now, turn out to be easy to tame if you have the right tools. Meanwhile, other seemingly simple functions occasionally turn out to be beasts. But this can also be fun, so happy hunting. Welcome to Module 2 of this course on calculus. As I mentioned at the end of the first module, if you're happy with the concept of differentiation, then in many ways everything we add from here will just be extensions of this core idea, as well as some interesting applications. The title of this course is Multivariate Calculus, so you won't be surprised to hear that we are now going to generalize the concept of gradients to multivariable systems. The words multivariable and multivariate are typically used interchangeably, and I will undoubtedly be using both in this module. There is, however, a subtle difference between these two terms, which is related to whether there are multiple input variables or multiple output variables, or both. But this distinction is not critical in the study of calculus that we're doing here, so we can leave it to the statisticians to sweat over. With more than one variable to play with, we will now be able to use calculus to help us navigate around high-dimensional spaces, and hopefully by the end of the module, we'll find some treasure. See you then. In the first module, we started by trying to develop a strong visual intuition relating derivatives to the gradient of a function at each point. We then followed this up by describing 4 handy rules to help speed up the process of finding derivatives. However, all of the examples we looked at were for systems involving a single variable. So now we're going to have to see what happens when we apply the same idea to systems with many variables, known as multivariate systems. But before we do that, we need to talk about what a variable is in the first place. Previously, we've shown examples of problems where one of the variables is a function of the other, i.e. y equals f of x. But where it wouldn't necessarily make sense to say that x equals g of y. For example, a vehicle's speed is clearly a function of time, as at each time the vehicle can only have one speed. However, we could not say that the time was a function of the vehicle's speed, as there might be multiple times at which the vehicle was travelling at any given speed. This is why we typically refer to the speed as a dependent variable, as it depends on time, and so time can be thought of as an independent variable in this particular context. Typically, when you first learn calculus, you take functions containing variables and constants, and then differentiate the dependent variables, such as speed, with respect to independent variables like time. However, what gets labelled as a constant or a variable can be subtler than you might think and will require you to understand the context of the problem being described. Let's continue using the example of a car to see how this might come up. Consider the following highly simplified expression relating the force F generated by a car's engine to its mass m, acceleration a, aerodynamic drag d, and velocity v. If you're driving a car, then you can change your speed and acceleration by pressing the accelerator pedal to adjust the force. But the mass and the drag are fixed features of the car's design. This means that we would call the force an independent variable as you control it directly, but your speed and acceleration depend on the variables as they are consequences of your applied force. Your mass and drag coefficients are clearly constants in this context. However, if you are a car designer looking to design each engine size in a new fleet, perhaps your market research has given you a specific acceleration and speed target. So in this context now, your force is still the independent variable, but now speed and acceleration are constants, whereas the mass and drag have become variables which you can adjust by redesigning your car. We refer to these slightly confusing variable design constants as parameters. We often think of varying them as exploring a family of similar functions, rather than describing them as variables in their own right. But these are largely engineering distinctions and not the kind of thing that would worry a mathematician. As you will see later in this course, when fitting functions to some data, it's the parameters of our fitting function which we are varying to find the best fit, which means that we'll have to differentiate with respect to these parameters. There is still some logic at work here, but my advice to you is just don't worry about it too much. The key takeaway here is you can in principle differentiate any term with respect to any other, so don't get caught off guard when things you thought were constants suddenly start to vary. Let's now look at a different example. Imagine that you wanted to manufacture a metal can. So you need to understand the relationship between the various key design parameters. We can start by writing a reasonable approximation for the can's empty mass m by breaking the area down into pieces. So the circles on top and bottom are pi r squared each, and when we unroll the body we get a rectangle where the width must be the same as the circumference of the circle, i.e. 2 pi r, and we'll just call the height h. So, taking these areas and multiplying them by a thickness t, we get the total volume of metal in the can. Finally, multiplying this by the metal's density, ρ, we get its mass. So, we can say that the mass, m, is going to equal the area of these two little circles, pi r squared times 2, of course, plus the area of the rectangle in the middle, so that's the circumference, 2 pi r, multiplied by the height h, and both of these are going to be multiplied by the thickness t and the density ρ. So t ρ and t ρ. I've written it in this long form here to make life a bit easier later on. At this point, what should we label as a constant or a variable? Well, with the exception of pi, which is definitely a constant for this universe, it's not entirely clear. We could in principle change any of the radius, the height, the wall thickness, even the material's density. So let's find the derivative of the can's mass with respect to each of them. To calculate these, all we do is, when differentiating with respect to a certain variable, simply consider all of the others to behave as constants. So, starting with an easy one, let's try h. So dm by dh is going to equal this thing, 2 pi r t ρ. As the first term did not contain the variable h, and we're treating all the other terms as constants, then just like last week, a constant simply differentiates to 0, so we ignored it. Whereas for the second term, it does contain h, and so it's just multiplied by some constants, so differentiating this just leaves those constants. We can see from this expression that the partial derivative with respect to h no longer even contains h, which is what you would expect, as the mass will vary linearly with the height when all else is kept constant. Notice that instead of using the normal d that we saw from doing derivatives in last module, we must use the curly partial symbol, which signifies that you've differentiated a function of more than one variable. Let's now find the partial derivative with respect to the other variables, starting with r. So partial m by partial r is going to equal, so there's an r squared term here which differentiates to 2r, so we're going to have 4 pi r t ρ, and this term just contains an r, so the r disappears, 2 pi h t ρ. Next we're going to do the variable t, and we can say dm by dt is going to equal, well there's just a t in here so it's not very exciting, 2 pi r squared ρ plus 2 pi r h ρ. And finally, all we've got left is ρ, so we can say dm by d ρ is just going to equal 2 pi r squared t, 2 pi r squared t, and 2 pi r ht plus 2 pi r ht. And really, although this is quite a straightforward example, that's basically it for partial differentiation. It's no more complicated than univariate calculus we met last module, the only difference being that you have to be careful to keep track of what you're considering to be held constant when you take each derivative. I hope this short introduction to multivariate calculus has helped you see that this concept is nothing to be intimidated by. Partial differentiation is essentially just taking a multidimensional problem and pretending that it's just a standard 1D problem when we consider each variable separately. I look forward to showing you the pretty amazing things that we can use this concept for later in the module. See you then. We've already seen how to think about partial differentiation as just a simple extension of the single variable method that we derived in the last module. In this video, we're going to explore some slightly more complicated partial differential examples, and we're also going to build something called the total derivative of a function. So, let's dive straight into a slightly more tricky problem than we saw last time. Consider the function f of x, y, and z equals sine of x e to the power of y z squared. We're now just going to work through and find the derivatives with respect to each of these three variables. So, let's start with x. As the exponential term does not refer to x, we can treat it as a constant, and sine, as we saw last week, differentiates to cosine. So we can write df by dx is just going to equal cos x e to the y z squared. Next, we'll differentiate with respect to y. In this case, the sine term does not refer to y, so we treat this as a constant, but for the exponential term, we can either apply the chain rule to it, or just remember that the result of this operation for an exponential will just be to multiply the derivative of the exponent to the front. And the derivative of yz squared with respect to y is just z squared. So we can write df by dy is going to equal sine of x e to the yz squared multiplied by z squared. Lastly, we'll differentiate with respect to z. Once again, the only z is in the exponential term, so similar to the previous example, we simply multiply through by the derivative of the exponential with respect to z. So we just get df by dz is going to equal sine x once again e to the yz squared, and this time the derivative of this thing is 2yz. So, now that we have these three partial derivatives, we're going to introduce a new idea called the total derivative. Imagine that the variables x, y, and z were actually all themselves a function of a single other parameter t, where x equals t minus 1, y equals t squared, and z equals 1 over t. And what we're looking for is the derivative of x with respect to t. In this simple case, we could just substitute for all our three variables directly in terms of t, simplify a little bit, and then differentiate directly with respect to t, which gives us sine of t minus 1 times e. However, in a more complicated scenario with many variables, the expression we needed to differentiate might have become unmanageably complex, and perhaps we won't have a nice analytical expression at all. The alternative approach is to once again use the logic of chain rule to solve this problem, where the derivative with respect to our new variable t is the sum of the chains of the other three variables, as shown in this expression. Since we've already got our three partial derivatives of f with respect to x, y, and z, now we just need to find the derivatives of the three variables with respect to t, and we'll have all the things we need to evaluate our expression. So, dx by dt is clearly 1, dy by dt is 2t, and dz by dt, if you remember from our 1 over t example, is minus t to the power of minus 2. Nothing hugely complicated here. However, when we then sub it into our total derivative expression, you can probably see why I've chosen not to write this all out by hand, as at first the expression is a bit of a monster. However, after substituting for x, y, and z all in terms of t, and then simplifying down again, we can see that the second and third terms are the same, just with opposite signs, and so they will cancel each other out. Then, kind of amazingly, we arrive at the same result as we saw at the beginning of the lecture. So, hopefully now you'll be feeling reasonably comfortable with partial differentiation, as we've already done quite a lot of it, and maybe you can even see why the total derivative function might be quite handy. You are now ready to have a go yourselves in the following exercises, and then you'll have all the pieces that you'll need in place for us to build our partial derivatives into something really useful. See you then. Previously, we saw that we can differentiate functions of multiple variables, and that it isn't much harder than the univariate calculus we met at the start of the course. In this video, we're going to introduce the Jacobian, which brings in some of the ideas from linear algebra to build these partial derivatives into something particularly useful. The concept of the Jacobian can be applied to a variety of different problems, but in the context of getting started with optimization and machine learning, there is a particular scenario that comes up a lot, which is the Jacobian of a single function of many variables. In short, if you have a function of many variables, so f of x1, x2, x3, etc., then the Jacobian is simply a vector where each entry is the partial derivative of f with respect to each one of those variables in turn. By convention, we write this as a row vector rather than a column vector, for reasons that will become clear later in the course. Let's start by looking at a nice simple function to see just how straightforward building a Jacobian can be. Consider the function f of x, y, and z equals x squared y plus 3z. To build the Jacobian, we just find each of the partial derivatives of the function one by one. So we've got df by dx is going to equal, we're just differentiating with respect to x, so we get 2xy when we treat everything else as constants. df by dy is going to equal just x squared, and df by dz is just going to be, so this thing's just a constant and the z disappears, so we just get the number 3. Now, bringing all of those together, we just end up with a Jacobian j, which is just going to be 2xy x squared 3. So, what does this tell us? We now have an algebraic expression for a vector which, when we give it a specific xyz coordinate, will return a vector pointing in the direction of steepest slope of this function. The vector for this particular function has a constant contribution in the z direction, which does not depend on the location selected. For example, at the point 0, 0, 0, we can see that our Jacobian is just going to be j of 0, 0, 0 is just going to be, well, 0, 0 again, but the number 3 over here. So we can see that our Jacobian is a vector of length 3 pointing directly in the z direction. Some of the numerical methods that we will discuss later in this course require us to calculate Jacobians in hundreds of dimensions. However, even for the 3D example we just solved, graphical representation is already quite difficult. So we are now going to drop down to 2 dimensions so that we can actually see what's going on here. But to keep things interesting, we're going to look at a particularly complicated but rather attractive function. So here is the equation that we're going to plot. But I'm showing it to you briefly just so that you can see that even though it is a bit of a monster, I hope you would agree that just with the tools we've seen so far, we really could calculate the partial derivatives of this thing. But you wouldn't really learn anything new from grinding through this. Instead, I'm going to show you the results graphically. So here is this function with the x-axis horizontal and the y-axis vertical, and the colours are indicating the value of z, with the bright regions suggesting high values and the dark regions suggesting low values. Because of the nature of this particular function, I know that nothing interesting happens outside of the regions shown here, so we can forget about it for now. Although this plot is fairly clear, our intuition about the gradient is a bit lacking in this format. So let's briefly make things 3D, where the values of z are now also represented by the height. So, as we said at the start of the video, the Jacobian is simply a vector that we can calculate for each location on this plot, which points in the direction of the steepest uphill slope. Furthermore, the steeper the slope, the greater the magnitude of the Jacobian at that point. Hold the image of this 3D space in your mind as we now go back to 2D. And rather than showing all of the grid points I used to plot the graph, let's instead convert to a contour plot, where just like a map of actual mountains, we will draw lines along the regions of the same height, which for us means the same value of z. This removes a lot of the clutter from the plot, which is useful for the final step that I'd like to show you, which will be adding lots of Jacobian vectors on top of our contour plot. However, before I do that, let's take a look at these 4 points and see if your intuition is now in tune by guessing which one will have the Jacobian with the largest magnitude. Overlaying the Jacobian vector field, we can see that they are clearly all pointing uphill, away from the low dark regions and towards the high bright regions. Also, we see that where the contour lines are tightly packed, this is where we find our largest Jacobian vectors, such as at point A. Whereas at the peaks of the mountains and at the bottom of the valleys, or even out on the wide flat plains, our gradients, and therefore our Jacobians, are small. My hope is that this clear two-dimensional example will give you the confidence to trust the maths when we come up against much higher dimensional problems later in the course. See you then. So, now that you've all spent some time playing in the sandpit, we can introduce an additional concept which relates to multivariate systems called the Hessian. In many ways, the Hessian can be thought of as a simple extension of the Jacobian vector. For the Jacobian, we collected together all of the first-order derivatives of a function into a vector. Now, we're going to collect all of the second-order derivatives together into a matrix, which for a function of n variables would look like this. However, this is one of those scenarios where using an abbreviated notation style comes in really handy. We saw in the previous module that we can just keep differentiating a function using the same method to find higher and higher order derivatives. Similarly, for a partial derivative, if you want to find the second derivative with respect to x1, then x2, it's as simple as just differentiating with respect to x1, assuming all the other variables are constant, and then differentiating with respect to x2, again, assuming all the other variables are constant. As you can see, from this general form, our Hessian matrix will be an n by n square matrix, where n is the number of variables in our function f. Let's now take a look at a quick example. It often makes life easier to find the Jacobian first and then differentiate its terms again to find the Hessian. So, for our function, f of x, y, and z equals x squared yz. So, f of x, y, z equals x squared y z. We're going to first build the Jacobian for this thing, which of course is going to be j equals, so we've got differentiate with respect to x, we get 2x y z. Differentiate with respect to y, we're just going to get x squared z, and differentiate with respect to z, x squared y. Now, using this, we can then think about differentiating again with respect to each of the variables, which will then give us our Hessian matrix. So H is just going to equal, we'll put a big bracket here. So we want to take this thing and differentiate it with respect to x again. So we're going to get 2yz. So the next term along, we're going to differentiate this thing with respect to y. 2xz, and again with respect to z, 2xy. Okay, now we'll take the next row and we'll say we're going to differentiate this thing with respect to x, then y, then z. So you get 2xz. We're going to differentiate with respect to y, so we're going to get nothing. And we're going to differentiate this thing with respect to z, and we get x squared. Lastly, take this term, make the last row, differentiate with respect to x, we get 2xy. And then with respect to y, we get x squared. And with respect to z, we get nothing. So, one thing to notice here is that our Hessian matrix is symmetrical across the leading diagonal. So actually, once I'd worked out the top right region, I could just have written these directly in for the bottom left region. This will always be true if the function is continuous, meaning that it has no sudden step changes. We could now simply pass our Hessian an x, y, z coordinate, and it will return a matrix of numbers which hopefully tells us something about that point in the space. In order to visualize this, we're going to have to drop down to 2 dimensions again. Consider the simple function f of x and y equals x squared plus y squared. Calculating the Jacobian and the Hessian are both fairly straightforward, and hopefully you could have visualized how this function would have looked in your head. However, if you hadn't known what function we were dealing with and calculated the value of the Jacobian at the point 0, 0, you'd have seen that the gradient vector was also 0. But how would you know whether this thing was a maximum or a minimum at that point? You could of course go and check some other point and see if it was above or below, but this isn't very robust. Instead, we can look at the Hessian, which in this simple case is no longer even a function of x or y. Its determinant is clearly just 2 times 2 minus 0 times 0, which is 4. The power of the Hessian is firstly that if its determinant is positive, we know we are dealing with either a maximum or a minimum. Secondly, we then just look at the first term, which is sitting at the top left-hand corner of the Hessian. If this guy is also positive, we know we've got a minimum, as in this particular case. Whereas if it's negative, we've got a maximum. Lastly, slightly modifying our function to include a minus sign and recalculating our Jacobian and our Hessian determinant, we now see the third interesting case. This time our Hessian determinant is negative, so we know that we're not dealing with a maximum or a minimum. But clearly at this point 0, 0, the gradient is flat. So what's going on? Well, if you look at the animation, what we've got here is a location with 0 gradient, but with slopes coming down towards it in one direction, but up towards it in the other. We call this kind of feature a saddle point, and they can also cause a lot of confusion when searching for a peak. In the last module of this course, you're also going to see another way that the Hessian can help us with optimization. But for now, we've simply got another tool to help you navigate the sandpit. See you next time. In this video, we're going to extend the concept of the Jacobian from vectors up to matrices, which will allow us to describe the rates of change of a vector-valued function. However, before we do this, we are first going to recap by applying what we've learned so far about Jacobians to another simple system. If we consider the function f of x and y equals e to the power of minus x squared plus y squared, then using our knowledge of partial differentiation, it's fairly straightforward to find its Jacobian vector. So we're now going to do the reverse of our approach from the last time and start by looking at the vector field of the Jacobians. Then see if we can understand how the function must look. Let's start by finding the Jacobian at a few specific points. Firstly, the point minus 1, 1, which we'll highlight on our axis in pink. Substituting these coordinates into our Jacobian expression and simplifying, we can see a vector pointing directly towards the origin. Next, if we move further out to the point 2, 2, find the Jacobian, we now get a much smaller vector, but pointing once again directly at the origin. Lastly, before I reveal the whole vector field, let's look at what's going on at the origin itself. Subbing the point 0, 0 returns the 0 vector, suggesting that the function is flat at this point, which must mean one of 3 things. Either this point is a maximum, minimum, or something called a saddle, which we'll cover later in this module. However, if we now reveal the rest of the Jacobian vector field, it becomes clear that the origin must be the maximum of this system. Let's now move back to the color map representation of this function, where the brighter regions represent high values of f. So, finally, we can remove the vector field and observe the function in 3D, which I hope matches up with your expectations. Next, we're going to build a Jacobian matrix which describes functions that take a vector as an input, but unlike our previous examples, also give a vector as the output. If we consider the two functions u of x and y equals x plus 2y and v of x and y equals 3y minus 2x, we can think of these as two vector spaces, one containing vectors with coordinates in uv and the other with coordinates in x and y. Each point in x, y has a corresponding location in uv. So, as we move around xy space, we would expect our corresponding path in uv space to be quite different, and so it is. For those of you familiar with the linear algebra, you may have guessed already where this is going. We can of course make separate row vector Jacobians for u and v. However, as we are considering u and v to be components of a single vector, it makes more sense to extend our Jacobian by stacking these vectors as rows of a matrix, like this. So, now that we have the structure and motivation for building a Jacobian matrix for vector-valued functions, let's apply this to our example functions and see what we get. So we have u of x, y equals x minus 2y, and we've also got v of xy equals 3y minus 2x. We can build the Jacobian from these two by simply saying, well, the Jacobian is going to be, let's open some big brackets and say, well, it's du dx, du dy, dv dx, dv dy. So let's just work through it. So du dx is just going to be 1. Du dy is just minus 2. dv dx is minus 2 again. And dv dy is 3. Our Jacobian matrix no longer even contains any variables, which is what we should expect when we consider that clearly both u and v are linear functions of x and y, so the gradient must be constant everywhere. Also, this matrix is just the linear transformation from xy space to uv space. So if we were to apply the xy vector 2, 3, we'd get the following. 2, 3, and that's going to equal 2 minus 6, that's minus 4, and minus 4 plus 9, that's 5. Now, this is all well and good, but of course many of the functions that you'll be confronted with will be highly non-linear, and generally much more complicated than the simple linear example that we've just looked at here. However, often they may still be smooth, which means that if we zoom in close enough, we can consider each little region of space to be approximately linear, and therefore, by adding up all the contributions from the Jacobian determinants at each point in space, we can still calculate the change in the size of a region after transformation. A classic example of this occurs when transforming between Cartesian and polar coordinate systems. So if we have a vector expressed in terms of a radius r and the angle up from the x-axis theta, but we'd like them expressed in terms of x and y instead, we can write the following expressions just by thinking about trigonometry. Now we can build the Jacobian matrix and take its determinant. The fact that the result is simply the radius r and not the function theta tells us that as we move along r away from the origin, small regions of space will scale as a function of r, which I hope will make a lot of sense to you when we look at our little animation here. That's all for this video. I hope you will now be able to build Jacobian vectors and matrices for yourself with confidence in the exercises, and more importantly, that your intuition on the meaning of this concept is starting to develop. See you next time. We've now seen that the Jacobian describes the gradient of a multivariable system, and that if you calculate it for a scalar-valued multivariable function, you get a row vector pointing up the direction of greatest slope, with a length proportional to the local steepness. In this video, I'm going to briefly introduce a kind of gradient playground to help you further develop your intuition on the Jacobian, which will also set you up for the following exercises. In everyday language, we use the word optimization to describe the process of trying to make something as good as it can be. In mathematics, optimization basically means the same thing, as much of the research is dedicated to finding the input values to functions which correspond to either a maximum or a minimum of a system. Examples of mathematical optimization in action in the real world include the planning of routes through busy cities, the scheduling of production in a factory, or strategy for selecting stocks when trading. If we go back to the simplest function we saw in the last section, and we said that we wanted to find the location of the maximum, we could simply solve this system analytically by first building the Jacobian and then finding the values of x and y which make it equal to 0. However, when the function gets a bit more complicated, finding the maximum or minimum can get a bit tricky. If, as in this case, we still have an analytical expression, then we can at least still find the general expression for the Jacobian. But now simply setting it to 0 is not only much more complicated, but it also is not enough, as this function has multiple locations with 0 gradient. If we assume that all of the maxima and minima of this function can be seen in the region that we're plotting here, then just looking at the surface plot of our function makes it very clear where the tallest peak and deepest trough are. We refer to all the peaks as maxima, but in this case we have a single tallest peak, A, which we will call the global maximum, as well as several local maxima at C and E. Similarly, we refer to all the troughs as minima, and we also have a single deepest point at D, which we call the global minimum, as well as a local minimum at point B. All fairly straightforward. However, there's a very important point here that's perhaps so obvious that you might have missed it. Imagine standing on the surface with its hills and valleys, and we're trying to climb to the top of the highest peak. That's no problem. We just look around, spot the tallest mountain, and walk straight towards it. But what if we were walking at night? This would be much like the scenario where we didn't have a nice analytical expression for our function, so we simply aren't able to plot the whole function and look around. Perhaps each data point is the result of a week-long simulation on a supercomputer, or maybe the outcome of an actual real-world experiment. These nighttime scenarios very commonly arise in optimization and can be very challenging to solve. However, if we're lucky, we might find that using a torch, we can see the Jacobian vectors painted on road signs all around us, and each one would say, peak this way. We would have to remember that although the Jacobians all point uphill, they don't necessarily point to the top of the tallest hill, and you could find yourself walking up to one of the local maxima at C or E. And even worse, when you get there, you'll find that all of the road signs are pointing directly at you. This nighttime hill walking analogy is often used when discussing the problem of optimization. However, it does have some misleading features, such as the fact that when you're really evaluating a function, it's no problem to effectively transport all over the map by teleportation, as you can try the function at many different places, but there's no need to evaluate everywhere in between. And the calculation costs the same, essentially, no matter how far apart the points are. So we're not really walking. Instead, we're going to switch to the analogy of a sandpit with an uneven base. In the following exercises, you're going to try to find the deepest point of a sandpit by measuring the depth at various points using a long stick. This is a very deep sandpit, so once you push the stick down to the bottom, there's no way to move it around sideways. You just have to pull it out and try somewhere else. Also, crucially, just like our night walking scenario, you will have no idea what the peaks and troughs look like at the bottom of the pit, because you can't see, the sand is in the way. As you work through the exercise, I'm hoping that you'll start to pick up on a few of the subtleties of optimization, and hopefully leave you with a few new questions as well. See you next time, and have fun in the sandpit. In this module, we've discussed how to think about two-dimensional functions as landscapes, and we've also seen that we can construct Jacobian vectors which tell us both the direction and the magnitude of the gradient at each point in space. Last video, we added one further tool to our toolbox, which allowed us to double-check what kind of feature we were standing on when we landed on a point with a zero gradient. These concepts will all be very useful to develop your understanding of optimization problems and have also let you see why multivariate calculus is worth knowing. However, in this video we are going to remind ourselves about two features of real systems which so far we've avoided. Firstly, for many applications of optimization, such as in the training of neural networks, you are going to be dealing with a lot more than 2 dimensions, potentially hundreds or thousands of dimensions. This means that we can no longer draw our nice surface and climb its mountains. All the same math still applies, but we now have to use our 2D intuition to guide us and enable us to trust the maths. Secondly, as we mentioned briefly before, even if you do just have a 2D problem, very often you might not have a nice analytical function to describe it, and calculating each point could be very expensive. So even though, in principle, a plot could possibly be drawn, you wouldn't be able to afford either the supercomputer time or perhaps the laboratory staff to fully populate this thing. Thirdly, all the lovely functions that we've dealt with so far were smooth and well behaved. However, what if our function contains a sharp feature like a discontinuity? This would certainly make navigating the sandpit a bit more confusing. Lastly, there are a variety of factors that may result in a function being noisy, which, as I'm sure you can imagine, might make our Jacobian vectors pretty useless unless we were careful. So, this brings us nicely to the second topic in this video, which is a question that I hope you've all been screaming at your screens for the past few minutes. If, as I said a minute ago, we don't even have the function that we're trying to optimize, how on earth are we supposed to build a Jacobian out of the partial derivatives? This is an excellent question and leads us to another massive area of research called numerical methods. There are many problems which either don't have a nice explicit formula for the answer or do have a formula, but solving it directly would take until the end of time. To fight back against the universe mocking us in this way, we have developed a range of techniques that allow us to generate approximate solutions. One particular approach that is relevant to our discussion of the Jacobian actually takes us right back to the first few lectures on this course, where we defined the derivative. We started by using an approximation based on the rise of a run calculated over a finite interval, and then looked at what happens as this interval approached zero. All we're doing with the finite difference method is accepting that we're not going to work out the value of the function at every single point in space, so we're just going to use the points that we do have and build an approximation for the gradient based on that. In the example shown here, we have already calculated lots of points on this one-dimensional function, but clearly that's not going to be practical for higher dimensional scenarios. So all we do is take this logic one step further and say, if we start from an initial location and we would like to approximate the Jacobian, we will simply approximate each partial derivative in turn. So taking a small step in x allows us to calculate an approximate partial derivative in x, and a small step in y gives our approximate partial in y. Two things to bear in mind here. Firstly, how big should our little step be? Well, this has to be a balance, as if it's too big, you will make a bad approximation for reasons that I hope will be obvious by this point. But if it's too small, then we might run into some numerical issues. Just remember, when your computer calculates the value of the function at a point, it only stores it to a certain number of significant figures. So if your point is too close, your computer might not register any change at all. Second, as we mentioned earlier, what happens if your data is a bit noisy? To deal with this case, many different approaches have been developed, but perhaps the simplest is just to calculate the gradient using a few different step sizes and take some kind of average. This brings us to the end of this video. So I hope you can see that once we leave the world of nice, smooth functions and enter the real world of noisy data and computationally expensive functions, things start to get a lot more interesting. See you next time. Welcome to Module 3 of the course. In the previous two modules, we've seen how to differentiate functions in single and multivariable spaces, as well as hopefully developing some intuition about what's really going on when we do this. We've also learned a selection of useful tools for both rapidly calculating derivatives and for navigating high-dimensional spaces. In this module, we're going to upgrade the univariate chain rule so that it can tackle multivariate functions, and then see an example of where this might come in handy. See you then. In the last module, we saw something called the total derivative, which showed us that when we have a multivariable function, such as f of x, y, and z, but the variables x, y, and z were themselves each a function of some additional variable t, then if we want to calculate the derivative of f with respect to t, we can use this expression, which is simply the sum of the chains relating f to t through each of its three variables. This allowed us to calculate the result in a piecewise manner, rather than substituting everything in at the start, and computers are really good at solving piecewise problems quickly. What we're now going to do is generalize this concept and also simplify the notation a little. If we had a function f of n variables, x1, x2, x3, all the way up to xn, I can write this as just f of x, but now you'll notice that I've written the x in bold, just to help you remember that this x represents a sequence of variables, which we'll now more conveniently think of as an n-dimensional vector. Once again, each of the components of our x vector are themselves functions of some other variable t, and what we'd like to know is the derivative of f with respect to t. At this point, we're going to need some more space to write. So we'll keep our function f at the top, but you'll just have to remember that each component of x is also a function of t. Now we're looking to once again build an expression linking f to t through the sum of the chains of each of its variables. So we're going to need all the partial derivatives of f with respect to x, as well as the derivatives of each component of x with respect to t. Once again, we're going to store all of these objects in a pair of n-dimensional vectors. Finally, we're looking to build a multivariable chain rule expression, so we are looking to find the sum of the product of each pair of terms in the same position in each vector. Thinking back to our linear algebra, this is exactly what the dot product does. But there is no need for us to write out these vectors in full, so we can simply write the dot of our two multivariable derivative expressions. And that's it. We now have our generalized form of the multivariable chain rule expressed nice and neatly. So we can now update our list of tools to reflect this. But actually, although we've seen this in practice already in the last module, it's worth pointing out that all the rest of our time-saving rules already work for multivariate problems as they are. So we'll be ready to put these into practice very soon. See you then. Last video, we finished up with an expression for the multivariate chain rule. In this video, we're going to start by picking up one more little detail which you might have already spotted, and then follow this up by adding another link to our chain. If we have a function f of x, where x is a vector in which each term in x depends on t, which we can compactly write like this, we also have our compact form of the multivariate chain rule to go with it. What I hope you might have noticed last time is that our vector of partial derivatives, df by dx, is just the same as the Jacobian vector which we saw last module, except that we wrote it as a column instead of a row vector. So from our knowledge of linear algebra, we can say that df by dx must be the transpose of the Jacobian of f. The last thing to realize is that taking the dot product of two column vectors is the same operation as multiplying a row vector by a column vector. So finally, we can see that our old friend the Jacobian offers us perhaps the most convenient representation of the multivariate chain rule. Next, we're going to see that the chain rule still works for more than two links. To start us off, we'll work through a really quick univariate example where we're going to add in another function separating f from t. So we can say f of x is going to equal 5x, and we can have x of u now can equal 1 minus u, and u of t finally can be t squared. So we've got three functions, and we're separating f from t now by an extra step. Of course, we can just sub in each step into each other and find an expression for f as a function directly of t, where we say, well, it's going to be 5 of whatever x is, and x is 1 minus whatever u is, and u is t squared. So this thing goes to 5 minus 5t squared. And of course, we can now directly differentiate this thing and say df by dt equals minus 10t. Or we can apply a two-step chain rule and say the following. So we can have df by dt is going to equal df by dx times dx by du, and finally du by dt. Okay? Now subbing in for each of our terms, we just get, well, this thing's going to equal df by dt is, so df by dx is just 5. We're going to multiply that by dx by du, which is just minus 1. And finally, du by dt is just going to be 2t. So once again, we're going to recover the same answer, which is minus 10t. So we can see that this approach works for chains of univariate functions, and we could extend it out to as many intermediary functions between f and t as we'd like. But what about the multivariate case? Well, the chain rule does work here too, but we do just have to pay attention to a few extra details. Let's start by considering the function f of x of u of t again, where the function f takes the vector x as an input, but this time x is a vector-valued function, which also takes a vector u as its input. As the last video, the bold symbols indicate vectors. So u is again a vector-valued function, and it takes the scalar t as its input. Ultimately, we are still relating the scalar input t to a scalar output f, but we're doing this via two intermediary vector-valued functions, x and u. If once again we'd like to know the derivative of f with respect to t, we can essentially write the same expression as the univariate case, except that now several of our terms are in bold. We've already seen that differentiating the scalar-valued function f with respect to its input vector x gives us the Jacobian row vector. We've also seen that differentiating the vector-valued function u with respect to the scalar variable t gives us a column vector of derivatives. But what about the middle term, dx by du? Well, for the function x, we need to find the derivative of each of the two output variables with respect to each of the two input variables. So we end up with 4 terms in total, which, as we saw in the last module, can be conveniently arranged as a matrix. We still refer to this object as a Jacobian, so we can now say that the derivative of f with respect to t is the product of the Jacobian of f with the Jacobian of x and the derivative vector of u. Notice that the dimensions of these vectors and matrices, as shown here, are such that this operation is possible, and that they will return as scalar just as we expected. That's it for this video. I hope you're now starting to see the various threads of linear algebra and multivariate calculus weave together. See you in the next one. In this video, I'm going to introduce to you the concept of artificial neural networks in just enough detail that we will be ready to see how the multivariate chain rule is crucial for bringing them to life. I think it's safe to assume that everyone watching this video will at least have heard of neural networks, and you're probably also aware that they've turned out to be an extremely powerful tool when applied to a wide variety of important real-world problems, including image recognition and language translation. But how do they work? You will often see nice diagrams like this one, where the circles are our neurons and the lines are the network of connections between them. This may sound a long way removed from the topics we've covered so far, but fundamentally, a neural network is just a mathematical function, which takes a variable in and gives you another variable back, where both of these variables could be vectors. Let's now have a look at the simplest possible case so that we can translate these diagrams into some formulae. Here, we have a network which takes in a single scalar variable, which we'll call a0, and returns another scalar, a1. We can write this function down as follows. a1 equals sigma of w times a0 plus b, where b and w are just numbers. But sigma is itself a function. It's useful at this point to give each of these terms a name, as it will help you keep track of what's going on when things get a bit more complicated. So our a terms are called activities, w is a weight, b is a bias, and sigma is what we call an activation function. Now, you might be thinking, how come all the terms use a sensible letter except for sigma? But the answer to this comes from the fact that it is sigma that gives neural networks their association to the brain. Neurons in the brain receive information from their neighbors through chemical and electrical stimulation, and when the sum of all these stimulations goes beyond a certain threshold amount, the neuron is suddenly activated and starts stimulating its neighbors in turn. An example of a function which has this thresholding property is the hyperbolic tangent function, tanh, which is a nice, well-behaved function with a range from -1 to 1. You may not have met tanh before, but it's just the ratio of some exponential terms and nothing your calculus tools can't already handle. Tanh actually belongs to a family of similar functions, all with this characteristic S shape called sigmoids, hence why we use sigma for this term. So here we are with our nonlinear function that we could evaluate on a calculator and also now know what all the terms are called. At the start of this video, I mentioned that neural networks could, for example, be used for image recognition. But so far, our network, with its two scalar parameters w and b, doesn't look like it could do anything particularly interesting. So what do we need to add? Well, the short answer is more neurons. So now, we're just going to start building up some more complexity whilst keeping track of how the notation adapts to cope. If we now add an additional neuron to our input layer, we can still call this scalar output variable a1, but we will need to be able to tell the difference between the two inputs. So we can call them a00 and a01. To include this new input in our equation, we simply say that a1 equals sigma of the sum of these two inputs, each multiplied by their own weighting plus the bias. As you can see, each link in our network is associated with a weight, so we can even add these to our diagram. Adding a third node to our input layer, A03, follows the same logic, and we just add this weighting value to our sum. However, things are starting to get a bit messy. So let's now generalize our expression to take n inputs, for which we can just use the summation notation, or, even better, notice that each input has a weight, so we can make a vector of weights and a vector of inputs, and then just take their dot product to achieve the same effect. We can now have as many inputs as we want in our input vector, so let's now apply the same logic to the outputs. Adding a second output neuron, we'd call these two values A10 and A11, where we now have twice the number of connectors, each one with its own weighting, and each neuron has its own bias. So we can write a pair of equations to describe this scenario, with one for each of the outputs, where each equation contains the same values of A0, but each has a different bias and vector of weights. Unsurprisingly, we can again crunch these two equations down to a more compact vector form, where the two outputs are each rows of a column vector, meaning that we now hold our two weight vectors in a weight matrix, and our two biases in a bias vector. Now, let's have a look at what our compact equation contains in all its glory. For what we call a single layer neural network with m outputs and n inputs, we can fully describe the function it represents with this equation. And peering inside, we can see all the weights and biases at work. The last piece of the puzzle is that, as we saw at the very beginning, neural networks often have one or several layers of neurons between the inputs and the outputs. We refer to these as hidden layers, and they behave in exactly the same way as we've seen so far, except that their outputs are now the inputs of the next layer. And with that, we have all the linear algebra in place for us to calculate the outputs of a simple feed-forward neural network. However, persuading your network to do something interesting, such as image recognition, then becomes a matter of teaching it all the right weights and biases, which is what we're going to be looking at in the next video, as we will bring the multivariate chain rule into play. See you then. In the previous video, we introduced the concept of neural networks, and then we worked through the algebra required to describe a fully connected feed-forward network with hidden layers. In this video, we're going to see how the multivariate chain rule will enable us to iteratively update the values of all the weights and biases, such that the network learns to classify input data based on a set of training examples. When we say that we are training a network, we typically mean using some kind of labeled data, which are pairs of matching inputs and outputs. For example, if we were to build a network to recognize pictures of faces and predict if they were happy, then for our training data, each of the inputs might be the intensity of a single pixel from the image, and this would be paired with an output, which just says whether this image contains a face and whether it was a happy face. The classic training method is called backpropagation, because it looks first at the output neurons and then works back through the network. If we start by choosing a simple structure, such as the one shown here, with 4 input units, 3 units in the hidden layer, and 2 units in the output layer, what we're trying to do is find the 18 weights and 5 biases that cause our network to best match the training inputs to their labels. Initially, we will set all of our weights and biases to be a random number, and so initially, when we pass some data into our network, what we get out will be meaningless. However, we can then define a cost function, which is simply the sum of the squares of the differences between the desired output, y, and the output that our untrained network currently gives us. If we were to focus on the relationship between one specific weight and the resulting cost function, it might look something like this, where if it's either too large or too small, the cost is high, but at one specific value, the cost is at a minimum. Now, based on our understanding of calculus, if we were somehow able to work out the gradient of c with respect to the variable w at some initial point w0, then we can simply head in the opposite direction. For example, at the point shown on the graph, the gradient is positive, and therefore increasing w would also increase the cost. So we should make w smaller to improve our network. However, at this point, it's worth noting that our cost function may look something more like this wiggly curve here, which has several local minima and is more complicated to navigate. Furthermore, this plot is just considering one of our weights in isolation, but what we'd really like to do is find the minimum of the multidimensional hypersurface, much like the 2D examples we saw in the previous module. So, Also like the previous module, if we want to head downhill, we will need to build the Jacobian by gathering together the partial derivatives of the cost function with respect to all of the relevant variables. So, now that we know what we're after, we just need to look again at our simple two-node network, and at this point, we could immediately write down a chain rule expression for the partial derivative of the cost with respect to either our weight or our bias. And I've highlighted the A1 term, which links these two derivatives. However, it's often convenient to make use of an additional term, which we'll call Z1, that will hold our weighted activation plus bias terms. This will allow us to think about differentiating the particular sigmoid function that we happen to choose separately. So, we must therefore include an additional link in our derivative chain. We now have the two chain rule expressions we'd require to navigate the two-dimensional WB space in order to minimize the cost of this simple network for a set of training examples. Clearly, things are going to get a little more complicated when we add more neurons, but fundamentally, we're still just applying the chain rule to link each of our weights and biases back to its effect on the cost, ultimately allowing us to train our network. In the following exercises, we're going to work through how to extend what we saw for the simple case to multi-layer networks. But I hope you've enjoyed already seeing calculus in action. See you next time. Welcome to Module 4 of the course. In this module, we're going to learn how to take a complicated function and build an approximation to it using a series of simpler functions. The particular approach that we're going to be looking at is known as the Taylor series, and it will require all of the calculus skills you've learnt so far to be put into practice. Both the Jacobian and the Hessian will be making appearances again when we consider the multivariate case, which will hopefully allow you to see how all of the concepts that you've seen so far are actually linked together. See you then. The Taylor series is one of a family of approaches used for building approximations to functions. So before diving into the maths, it's worth stopping for a minute to talk about when it might be useful to have an approximation. One example that seems to stick in people's minds is to do with cooking a chicken. Imagine that you could write a function which describes the relationship between the mass of a chicken, m, and the amount of time t it should be put in the oven before it would be perfectly cooked. Clearly, there are a lot of assumptions that we'd need to have in place for such a function to even exist. For example, this would only apply to a certain type of oven preheated to a certain temperature applied to a certain configuration of chicken, i.e. one that's in one piece rather than chopped up. Furthermore, the heat transfer properties of a chicken will almost certainly vary in a highly non-linear fashion as a function of the mass. Let's have a look at the sample function that has some of the features that we've mentioned. You can imagine that on the one hand, the chicken cooking time t will be quite sensitive to a lot of parameters that we might expect to vary case to case. However, on the other hand, if we'd like to sell a nice recipe book, we're going to need to be pragmatic and simplify this monster, as people tend not to want to solve complicated equations while making dinner. So, what do we do? Firstly, we're going to make two assumptions, one about ovens and the other about chickens. So let's assume that it's reasonable to suggest that everyone who buys your cookbook will have a sufficiently similar oven, such that we can assume that they behave basically the same. Secondly, that everyone will be cooking a sufficiently similar chicken in terms of their heat transfer properties as a function of mass, that you can also assume that these will be the same in each case. This allows us to remove two potentially problematic terms that might themselves have been a function of many other variables, but we were still left with quite a messy function. The next thing we're going to do is have a look at a plot of this function. Now, already I'm telling you about what I view as relevant information in this system, as I'm not showing you timings for chickens heavier than 4 kilograms or chickens of negative mass. And in fact, what I'm going to do now is go one step further and say that considering a typical chicken from a supermarket is about 1.5 kilograms, so let's focus here and build a nice straight line approximation of the form y equals mx plus c. By using the Taylor series approach, which we will be learning in the following videos, it is possible for me to derive a function with the same height and slope as one of the points in my graph. This line is a fairly reasonable approximation to the function in the region close to the point of interest. But as you move further away, the approximation becomes pretty poor. However, This cookbook is not for people either roasting giant or miniature chickens. So we end up being able to write down an expression in a much more palatable format, where our approximation T star is approximately equal to 50 times the mass in kilograms plus 15. So if you'd like to roast a 2-kilogram bird, leave it for about 115 minutes. In the next few videos, we're going to go into a lot more detail about the Taylor series and also find out how to derive higher order terms. I really don't know whether the famous chefs around the world are knowingly using Taylor series approximations when they write their cookbooks, but I like to think that they are. See you next time. In this short video, I'm just going to give you one more teaser about what the Taylor series is doing before we try and write down anything like a formal definition. This will allow you to have a go at some graphical questions first, which is much like how we approached learning differentiation at the start of this course. Taylor series are also referred to as power series, and this is because they are composed of coefficients in front of increasing powers of x. So we can write a simple generalized expression for a power series as g of x equals a plus bx plus cx squared plus dx cubed, etc. Potentially going off for infinitely many terms, depending on what function we're considering. When we calculate a Taylor series in the next video, we will build it up coefficient by coefficient, where each term that we add improves the approximation, and in many cases, we will then be able to see a pattern emerge in the coefficients, which thankfully saves us the trouble of calculating infinitely many terms. However, many of the applications of Taylor series involve making use of just the first few terms of the series in the hope that this will be a good enough approximation for a certain application. Starting from just a single term, we call these expressions the 0th, 1st, 2nd, and 3rd order approximations, etc. Collectively, these short sections of the series are called truncated series. So let's begin by looking at some arbitrary but fairly complicated function. If we start with something like this, where we have a function, and we're just making it up, perhaps shaped like this, all we're going to do is focus on one particular point on this curve. So let's say this point here. And then we're going to start building our function by trying to make it more and more like the point that we've chosen. So as the first term of our generalized power series is just a number, a, and we're ignoring all the other terms for now, we know that our opening approximation must just be a number that goes through the same point. So we can just dive straight in and add our 0th order approximation function to our plot. It's going to be something like that. Clearly, this hasn't done a great job at approximating the red curve. So let's now go to our 1st order approximation. This thing can also have a gradient, and if we'd like to match our function at this point, it should have the same gradient. So we can have something a bit more like this, which is supposed to be a straight line. Clearly, our approximation has improved a little in the region around our point, although there is still plenty of room for improvement. We can of course move on to the 2nd order function, which, as we can see, is a parabola, although at this point things get a little tough to draw, and matching second derivatives by eye is also not easy, but it might look something like this. So we can say, okay, let's go up, and we're going to come down like that. Hopefully, without having gone into any of the details about the maths, you'll now be able to match up some mystery functions to their corresponding truncated Taylor series approximations in the following exercise. In the next video, we're going to work through the detailed derivation of the terms, but I hope this activity will help you not to lose sight of what we're trying to achieve in the end. See you then. In this session, we're going to work through the derivation of power series representation of functions, which in short is the idea that you can use a series of increasing powers of x to re-express functions. Just to warm up by blowing your minds, we can take the function e to the x, which we met earlier in the course, and re-express it as the series 1 plus x squared over 2 plus x cubed over 6 plus higher order terms. Now, I hope you would agree with me that this is pretty incredible, and hopefully by the end of this video you will understand how to build series like this for many other interesting functions. What the Taylor series method tells us is that if we know everything about the function at some point, whereby everything, I mean the function's value, its first derivative, second derivative, third derivative, etc., then we can use this information to reconstruct the function everywhere else. So if I know everything about it at one place, I also know everything about it everywhere. However, this is only true for a certain type of function that we call well-behaved, which means functions that are continuous and that you can differentiate as many times as you want. That said, we know lots of functions like that, so it turns out to be a very useful tool indeed. So now we're going to try and explain this concept graphically by looking at a graph of some arbitrary function f of x, which looks like this, and building a sequence of gradually improving approximations. So, our first approximation, which we can call g0, we're going to build using just one piece of information from our function f of x, which will be the value of the function at our point of interest, which in this case is just x equals 0. As you can imagine, if all we're going to build our function off is this one single value, then clearly our guess function isn't going to be able to capture a very complicated shape like this. And in fact, all it can be is a horizontal line at the point f at 0. So we can plot this first approximation and also write an expression for calculating g0 of x, which is just f of 0. We call this our 0th order approximation, and clearly it's not very good. But also notice that as this line is flat, it's actually not even a function of x. We can do better. So let's now find our first order approximation. For this, we're now going to use two pieces of information, the value of the function at x equals 0, but also the value of the gradient at x equals 0, which we will call f dash at 0. Using these, we can build another straight line of the form y equals mx plus c, where the vertical axis intercept c is just f of 0, but just substituting in for f dash of 0 as the gradient of our line. So we can now plot our first order approximation to the function, which has the same value of the gradient and of the function f of x. And we can also write down its expression g1 of x is f of 0, f dash of 0 times x. This thing clearly does a better job than g0 at approximating f of x near the point x equals 0, but it's still not great. Moving quickly on to our second order approximation, g2 of x, we're going to use three pieces of information, f of 0, f dash of 0, and the second derivative f double dash of 0. Now, to have a function that can make use of these three pieces of information, we're going to need a quadratic equation. So we can write y equals ax squared plus bx plus c. Differentiating this thing twice, we can just say, well, y prime equals 2ax plus b, and y double prime equals 2a. Now what we want is for this function to be the same as f of x when we sub it in at the point equals 0, x equals 0. So we can say, okay, at x equals 0, we want this thing to equal f double prime of 0. So clearly, our coefficient a, because this thing's not even a function of x, therefore a is just going to equal f double dash 0 divided by 2. Now if we look up at this equation here, we also want the first derivative to be equal to the function at 0. So we can set this equal to f dash of 0, and we're subbing in 0 for this x here, so this term just disappears. So we can now say that also b equals f dash at 0. Lastly, subbing in 0 here, and setting this thing just equal to f of 0, we can say that clearly c is also just equal to f of 0. c equals f at 0. So we now have all three coefficients for our equation. And we can say, let's now go back to our graph and add our second order approximation, which, as it's just an x squared term, will be a parabola. Notice that each time we update our approximation, the region in which it matches up with f of x grows a little. So let's now take one more step down the rabbit hole and find the third order approximation. So we can write y equals ax cubed plus bx squared plus cx plus d. As based on what we've already seen from the first three steps, it's only the coefficient a that we need to find, as b, c, and d will be the same as we found for g2. So let's now differentiate this thing 3 times. Y prime equals 3ax squared plus 2bx plus c. Y double prime equals 6ax plus 2b. And y3 is just going to be 6a. So clearly, we want this thing, the third derivative of our approximation function, to equal our function f of x when we've differentiated it 3 times and evaluated at the point x equals 0. So we're setting this x to 0. Now there is no x in this bit. We can say f3 at 0 equals 6a. Therefore, a just equals f3 at 0 divided by 6. Finally, we can add this third order approximation to our graph and write out its expression. You can now see that not only has the approximation improved significantly, but also that we can add higher order terms piecewise, and in each case the lower order terms remain the same. What we now want to build is a general expression. The lower order terms remain to just write down the fourth order approximation without working through it. Notice that the 1/6 coefficient in front of the cubic term was the result of having to differentiate a cubic term twice. So when we differentiate x to the 4th power 3 times, we are going to get 4 times 3 times 2 in front, leading to a coefficient of 1 divided by 4 times 3 times 2, which is 1 divided by 24. We have a name for the operation 4 times 3 times 2, which is 4 factorial. And in fact, all the terms can be thought of as having a factorial in front of them, even 0 factorial, which, for reasons I won't go into here, is in fact equal to 1. So with this last piece of the puzzle in place, we can now say that the nth term in the approximation is just the nth derivative of f, evaluated at 0, divided by n factorial multiplied by x to the power of n. And therefore, the complete power series can be written as follows. So you can see it's the sum from n equals 0 to infinity of these terms. Although what we've written here certainly does count as a Taylor series, because we're specifically looking at the point x equals 0, we often refer to this case as a Maclaurin series. So you're still going to have to wait one more video before seeing the Taylor series expression in all its glory. In the rest of this module, we're going to be applying the concept of power series to some interesting cases, as well as generalizing it to higher dimensions, where rather than building approximation curves, we will be constructing approximation hypersurfaces. See you then. I began our last session by trying to motivate you with the fact that we can re-express the function e to the x as a power series. So I want to make sure that your mind is well and truly blown by showing you that when we differentiate this function term by term, which isn't very difficult to do as it's just a polynomial, something rather satisfying happens, where, just as we'd expect for the derivative of e to the x, this infinitely long series remains unchanged, which I think is pretty awesome. So now, finally, you're going to get to see the Taylor series. Fundamentally, we are applying the same logic as the Maclaurin series that we derived previously. But whereas the Maclaurin series says that if you know everything about a function at the point x equals 0, then you can reconstruct everything about it everywhere, the Taylor series simply acknowledges that there is nothing special about the point x equals 0, and so says that if you know everything about the function at any point, then you can reconstruct the function anywhere. So, a small change, but an important one. Let's look again at the function e to the x, as well as the first 4 approximation functions. Now, Using our understanding of the Maclaurin series, we can also rewrite this in a compact summation notation, such that we could, if we wanted, build a polynomial approximation function to an arbitrary degree of accuracy. So what if now, instead of expanding around the point x equals 0, we wanted to start from the point x equals p? Well, to begin with, let's have a look at the first 4 approximation functions at this point. The expressions to describe these approximations are still going to require the value of the function, as well as all of its derivatives at this point. But how do we now adjust our general equation to allow for an arbitrary expansion point, x equals p? Well, clearly, the 0th order term, this is just straightforward. It's going to be a horizontal line that just uses the point f of p everywhere. But what if we take a closer look at the first order approximation? This should give us enough insight that we'll then be able to tackle all the other higher order terms. So we're essentially looking to build a tangent to the curve at point P. All straight lines are of the form y equals mx plus c. So let's now work through this by putting in place all the information that's available to us. So we can say, okay, here is some nice function that we're going to deal with. And if we're looking at the point P here, this is of course at f of p height. So its coordinates of this point are p, f of p. And we want to build an approximation function that is first order. So it's got a y-axis intercept and it's got a gradient. And it's going to look something like this. Okay, the same gradient and the same height of the function at that point. So of course that green line is going to have the equation y equals mx plus c. Now we know immediately that m is the gradient of this straight line. And we know the gradient of our function here is just f dash at p. So we can say y equals f dash at p x plus c. So all that's left is for us to find c. And to do that, we're going to need to know x and y. But we do know a point on our line. It's the point p, f of p. So we just sub these in. F of p equals f dash of p at p plus c. Rearranging for c, we can just see that c is going to equal f of p minus f dash of p at p. Subbing the c back into our general equation, we can now bring it round and say, well, this line has the equation y equals m, which is just f dash of p, times x plus c, which is just f of p minus f dash of p multiplied by p. Okay? Now the last thing I'm going to do is take this and factorize this f dash of p out. And that'll leave you with a nice form of this expression. Y equals f dash of p multiplied by, there's an x of it here, and there's a minus 1 of it here, and minus p of it here. So we can say x minus p plus, just this term here, f of p. What this shows us is that by building our approximation around the point p, when we use our gradient term f dash of p, rather than applying it directly to x, we instead now apply it to x minus p, which you can think of as how far are you away from p. So we can now write down our first 2 approximation functions to f of x at the point p, the 0th and the 1st. Thinking back to the Maclaurin series from the previous video, all we need to do to convert to Taylor series is use the second derivative at p rather than 0, and also replace x with x minus p. But notice that the factor of 1/2 still remains. So we can now look at our concise summation notation for the Maclaurin series and upgrade the whole thing to the more general Taylor series form, noticing, of course, that if we decide to set p to 0, then the expressions would actually become identical. So we now have our one-dimensional Taylor series expression in all its glory, which will allow us to conveniently re-express functions into a polynomial series. In the remainder of this module, we're going to play around with this result, as well as extending it to higher dimensions. See you then. In this video, we're going to put our understanding of power series to the test by looking at two interesting examples. First off, we're going to build a Maclaurin series expansion of the cosine function. Cosine is the epitome of a well-behaved function, as it is certainly continuous everywhere, as well as being infinitely differentiable. As we're building a Maclaurin series, we're going to want to find out everything about the function at the point x equals 0. So let's start by doing some differentiation. And what we get, if you remember from earlier in the course, is this cyclic pattern of cosines and sines, positive and negative, which takes us back to the cosine again after 4 steps. If we now evaluate this derivative at the point x equals 0, we see that the cosine terms are either 1 or minus 1, and the sine terms are all 0. This must mean, from a power series perspective, that every other term will have a 0 coefficient. Notice that these zeros will occur whenever we differentiate an odd number of times, which means that all the odd powers of x, like x to the 1, x cubed, x to the 5, etc., will all be absent from the series. The even powers of x are all what we call even functions, which means that they are all symmetrical around the vertical axis, just like cosine is. So, we can now bring back our general expression for the Maclaurin series and just start writing out the terms. The icing on the cake is that at this point, we just notice that we can build a neat summation notation which fully describes this series without having to write out all the terms. Notice that this expression doesn't even contain any reference to cosine, as all that we need to know is captured by the minus 1 to the power of n, which just keeps flipping from negative to positive and negative again. Now that we've done all the hard work, we can simply ask our computer to plot this sequence of increasingly accurate Maclaurin series, which hopefully, starting from a horizontal line at y equals 1, will line up with your expectations. Notice that outside of a region of fairly close to the point x equals 0, the approximation explodes off and becomes useless. By the time we get our 16th order approximation, we've pretty much nailed the region shown in our graph here, although just outside of these axes, the function would also be growing hugely positive. So you must always be careful when handling series approximations that you know the domain in which it's acceptable. In the second example, we're going to take a look at the function f of x equals 1 over x, which of course looks like this. It's a nice, simple function, but notice the discontinuity at x equals 0. This is absolutely not a well-behaved function. In fact, it's so badly behaved that when we even try and build the 0th order approximation, we immediately run into problems, because we have to perform the operation 1 divided by 0, which is not defined. And if you tried to ask your computer to do this, it may give you back the answer nan, which stands for not a number. So, we're going to need to try a different angle of attack. Clearly, we aren't going to have much luck at the point x equals 0, so why not try going somewhere else, anywhere else? Let's look at the point x equals 1. Certainly, it passes the first test of being able to evaluate the function at this point. However, moving away from x equals 0 means that we're now going to need to use the Taylor series instead of the Maclaurin series. So we now need to find a few derivatives of the function and see if we can spot a pattern. When we evaluate these functions at the point x equals 1, hopefully you'll recognize that we get a sequence of factorials emerging, just as we did when deriving the power series formula in the first place. So if we now substitute these values into our Taylor series formula, the factorial terms will cancel, and all we are left with is a sum of x minus 1 to the power of n terms with alternating signs, which we can simplify to this neat summation notation. So once again, let's now pass this formula to the computer and ask it to plot a sequence of improving approximations, starting as ever with a horizontal line, but this time starting at the height of the function at x equals 1. There are several really interesting features of this particular example which tell you interesting things about the power series more generally. Firstly, the approximations ignore the asymptote, going straight across it. And furthermore, the region of the function where x is less than 0 is not described at all by the approximations. Secondly, although the function is gradually improving for larger values of x, you can see the tail wildly flailing around as the sign of each additional term flips from positive to negative and back again. I hope these two examples have made it clear both how the Taylor series manages to reconstruct well-behaved functions like cosine x, but also why they can struggle to deal with something badly behaved like 1 over x. As we bring this video to a close, let's now watch an action replay of these two sequences of improving approximations. In the next video, we're going to talk briefly about what it means to linearize a function and see how this relates to the Taylor series analysis that we've seen so far. See you then. In this session, we're just going to take what we've learned about Taylor series so far and reframe it to a form that will help us understand the expected error in an approximation. So, as we've already seen, we can build up a sequence of gradually improving approximations to functions by adding higher powered terms. All I'm going to do now is change the notation of some of the terms. So if we take our first order approximation as an example, what this expression is saying to us is starting from the height f of p, as you move away from p, your corresponding change in height is equal to your distance away from p times the gradient of your function at p. So in a sense, rather than using gradient equals rise over run, we are just rearranging to rise equals gradient times run. You are ultimately going to use your approximation to evaluate the function near p, as you must already know about it at p. So I'm now going to say that our distance from p, which we currently call x minus p, we will now call delta p, to signify that it represents a small step size away from p. And we can also recast x now in terms of p, saying that x is just p plus delta p. Finally, it actually is now time to say goodbye to p, as in our first order approximation, everything is actually in terms of p. So all I'm going to do is swap all the p's for x's, as this is the form that people would usually expect to see it in. I'm going to do it all at once to make it as painless as possible. I haven't changed anything conceptually, I've just written an x everywhere where we used to have a p. And we can now, of course, also rewrite our Taylor series expression in this new form, with just x and delta x. So we're in good shape to talk about approximations. What I now want to know is, when I use the first order approximation, instead of evaluating the base function, how big should I expect the error to be? You can see, for example, that the gap between the white and green lines grows as we move along the x-axis away from the point x. Well, one way to think about it is that we know our function can be exactly represented by this infinitely long series. So although we won't be able to evaluate all of the terms, we do know that the next term along, i.e. the first term that we ignore when we're using our first order approximation, has a delta x squared in it. This means that if we can say that delta x is a small number, then delta x squared must be a really small number, and similarly delta x cubed must be a ridiculously small number. So we can now rewrite our first order approximation to include an error term, which we just say is on the order of delta x squared, or equally, that it is second order accurate. This process of taking a function and ignoring the terms above delta x is referred to as linearization, and I hope it's now clear to you why that's the case. We've taken some potentially very nasty function and just approximated it with a straight line. The last idea that I'm going to share with you in this video is perhaps the most interesting, as it brings us right back to our rise over run approximation that we met at the beginning of the course. The green line is our first order Taylor series approximation to the function at the point x, which is of course also the tangent to the curve at x. But let's now add another line, which is the approximation to the gradient at x using our rise over run method with a second point delta x away. We use this forward difference method to help us build the definition of a derivative at the beginning of the course. And we noticed that as delta x goes to 0, the approximation becomes exact. However, what happens if delta x does not go to 0 and the second point remains some finite distance away from x? Well, your calculated gradient will now contain an error, and once again, we can rearrange the full Taylor series to work out how big we'd expect that error to be. With a bit of slightly fiddly algebra, we can rearrange this expression such that the gradient term f dash of x is isolated on the left-hand side. Because the series is infinite, this is still an exact expression for the gradient at x, but what we get on the right-hand side is something that looks suspiciously like the rise over run expression plus a collection of higher order terms. If we notice that the first of the higher order terms has a delta x in it, we know that we can now lump them all together and say that using the rise over run method between 2 points with a finite separation will give us an approximation to the gradient that contains an error proportional to delta x. Or, more simply put, the forward difference method is first order accurate. That's all for this video. It might seem a little odd to go to all that trouble just to get an idea of the error in an approximation, but it turns out to be a hugely important concept when, as is typical, we ask computers to solve numerically rather than analytically. See you next time. So far in this module, I've introduced you to the concept of power series and then shown you how we can use them to approximate functions. We've also seen how power series can then be used to give you some indication of the size of the error that results from using these approximations, which is very useful when applying numerical methods. The last idea that we're going to very briefly look at on this topic is upgrading the power series from the one-dimensional version that we've seen so far to its more general multivariate form. Just to recap on the notational options from the previous video, we saw that we can re-express the Taylor series from a form that emphasizes building the approximation of a function at a point P to a totally equivalent form that emphasizes using that function to evaluate other points that are a small distance delta x away. Just to make sure you can see that they're the same, we can write out the first 4 terms one above the other to make the comparison clear. In this video, we are going to continue using the delta x notation as it's more compact, which will come in handy when we're in higher dimensions. We won't be working through the multivariate Taylor series derivation in any detail, as all I really want you to take away from this video is what a multidimensional power series will look like, both as an equation and in a graph. So keeping in mind our one-dimensional expression, let's start by looking at the two-dimensional case, where f is now a function of the 2 variables x and y. So our truncated Taylor series expressions will enable us to approximate the function at some nearby point x plus delta x, y plus delta y. Let's look at the simple two-dimensional Gaussian function, which many of you may be familiar with from studying the normal distribution in statistics. It's a nice, well-behaved function with a simple maximum at the point 0, 0. Now, in a one-dimensional analysis, our power series would give us an expression for a one-dimensional function. However, in a two-dimensional case, our power series would of course now give us a two-dimensional function, which we would more intuitively refer to as a surface. Just as with the one-dimensional case, our 0th order approximation are simply the value of the function at that point applied everywhere. Which means in 2D, this would just be a flat surface. So a 0th order approximation at the peak would look like this. And a 0th order approximation somewhere on the side of the bell would look a bit more like this. This is fairly straightforward, but now let's think about the first order approximation. Drawing the analogy from the 1D case again, the first order approximation should have a height and a gradient. So we're still expecting a straight surface, but this time it can be at an angle. Now, if we are calculating it at the peak, it wouldn't be a very exciting case, as it's a turning point, and so the gradient is 0. However, let's look again at the point on the side of the slope. Taking the first order approximation here gives us a surface with the same height and gradient at the point. Finally, let's look at the second order approximation for these 2 points. We're now expecting some kind of parabolic surface. However, if I calculate it at the peak, nothing seems to appear. But that's just because we've created a parabola inside our bell curve. So we need to look from underneath to even see it. Finally, if we plot the second order approximation at the point on the side of the bell curve, you can see that we end up with some kind of interesting saddle function. But it's still fairly clear, even by eye, that the gradient and the curvature are matching up nicely at that point. Although this approximation is evidently not useful outside of a fairly small region around the point. We're now going to take a look at how we would write expressions for these functions. So, if we wanted to build a Taylor series expansion of the two-dimensional function f at the point x, y, and then use it to evaluate the function at the point x plus delta x, y, delta y, our 0th order approximation is just a flat surface with the same height as the function at our expansion point. The first order approximation incorporates the gradient information in the 2 directions. And once again, we are thinking about how rise equals the gradient times the run. Notice here, for compactness, I'm using the partial symbol with a subscript to signify a derivative with respect to a certain variable. If we look now at the second order approximation, we can see that the coefficient of 1/2 still remains as per the one-dimensional case, but now we have 3 terms, all of which are second derivatives. The first has been differentiated with respect to x twice, the last with respect to y twice, and the middle term has been differentiated with respect to each of x and y. Now, there are of course higher order terms, but we've already got more than enough to play with here. So, let's look again at the first order term. It's the sum of the product of the first derivatives with the step sizes. But hopefully, this will remind you of our discussion of the Jacobian. So we can actually re-express this as just the Jacobian multiplied by a vector containing delta x and delta y, which we can write as delta bold x, where the bold x signifies a vector containing those 2 terms. Finally, if we look at the second order term in the same way and notice that these second derivatives can be collected into a matrix, which we've previously defined as our Hessian, then to make the sum we need, we now have to multiply our delta x vector by the Hessian and then again by the transpose of the delta x vector. And that's it. So, we now have a nice compact expression for the second order multivariate Taylor series expansion, which brings together so much of our calculus and linear algebra skills and makes use of the Jacobian and Hessian concepts which we defined earlier in the course. And of course, although we've been talking about the 2-dimensional case in this video so far, we could actually have any number of dimensions contained in our j, h, and delta x terms. So this immediately generalizes from 2D to multidimensional hypersurfaces, which is pretty cool. See you in the next one.
Hi there, I'm David Dye and I'll be taking you through the last few modules of this course. In this module, we'll start to use the calculus we've done and put it together with vectors in order to start solving equations. In this first video, we'll look at a nice simple case where we just need to find the gradient, the derivative, in order to solve an equation using what's called the Newton-Raphson method. Now, say we've got that distribution of heights again with a mean, an average, mu, and a width, sigma. And we want to fit an equation to that distribution that, so we don't have to, after we've fitted it, bother about carrying around all the data points. We just have a model with 2 parameters, a mean and a width. And we can do everything using just the model. And that would be loads faster and simpler and would let us make predictions and so on. So it would be much, much nicer. But how do we find the right parameters for the model? How do we find the best mu and sigma we can? Well, what we're going to do is we're going to find some expression for how well the model fits the data, and then look at how that goodness of fit varies as the fitting parameters mu and sigma vary. So we're trying to solve an equation where the fitting parameters are the variables in the equation, but in order to get there, in the next module actually, we're first going to need to do a bit more calculus. So first, let's look at the equation of a line. Say here, y equals x cubed minus 2x plus 2. If we differentiate this equation, we get the quadratic 3x squared minus 2, and that quadratic will have 2 solutions, and therefore 2 turning points will exist, one a maximum, one a minimum, just as we see here. Now, say that I don't know what the equation looks like, I'm blind, and I haven't got enough computer resources to graph out the values at every point. Or more likely, in reality, say the function exists in so many dimensions that I can't visualize it at all. But say I only need to find the solution to the equation where y equals 0. So where x cubed minus 2x plus 2 is equal to 0. We can see that there's actually only one solution here on this graph, but there could be more depending on the exact form of the equation I was trying to solve. Now, say that I have an idea that I want to hunt for a solution somewhere near some initial guess, the red dot here. For instance, the constant's pretty small and positive, so I might guess that I need a slightly negative value of x, say minus 2 might be somewhere near a solution. Now, if I can evaluate the value of the function at my guess of x equals minus 2, I find that the function has a value of minus 2. And if I ask what the gradient is at that value of x equals minus 2, I find that the gradient is positive and it's 10. Now I can extrapolate the gradient to the intercept with the y-axis, which is would be my first guess of the solution of the equation. So I'm trying to solve where it finds that intercept with the y-axis. So I can use that value of x at the intercept as a new estimate for what the solution to the equation is. effectively I'm guessing that the function is a straight line, and then I'm using the gradient to extrapolate to find the solution. It isn't really a straight line, of course, but the first order approximation would be that it's a straight line, and we'll use that to update our guess and then go again and evaluate. So I can write down an equation for my new guess, xi plus 1, based on my previous guess at attempt xi, as being my original guess minus the value of the function divided by its gradient. So let's see how it plays out. We can make a table starting with our initial guess at I equals 0, and then we can find the gradient and the intercept. And then use that to generate a new guess. In this case, minus 2 minus minus 2 divided by 10 gives us minus 2 plus 0.2, which is minus 1.8. Then we can evaluate the result for that guess and find that it's just a little less than 0, minus 0.23, and the gradient is 7.7. So we've gone from being out by 2 on y to being out by just 0.23. So in some sense, we've got like 10 times better in our estimate, just in our first go. If we carry on, then we get the next guess for x2 is minus 1.77, and that's just 0.005 away from the axis. It's really close. Then if we have another go, after just 3 iterations, we get an answer of x equals minus 1.769, which is just 2.3 times 10 to the minus 6 from the axis. So in just 3 iterations, we've pretty much solved the problem, which is pretty cool. This method is called the Newton-Raphson method, and it's really pretty neat. To solve an equation, all we need to be able to do is evaluate it and differentiate it. We don't need to graph and visualize it everywhere, calculating it lots and lots of times. We don't need to be able to solve it algebraically either. Which if we have lots of dimensions to a data set, say, and a big multi-variable function we're trying to fit to that data, it's going to be much too expensive to try and solve it analytically, or even plot it out for all the possible values of the variables. This sort of method where we try a solution and evaluate it, and then generate a new guess, and then evaluate that, and again and again and again, is called iteration. And it's a very fundamental computational approach. Now, there are some things that can go wrong sometimes with this method, so let's briefly look at those. Say I started off with a guess of x equals 0, which evaluates to y equals 2. When I find the gradient for that and extrapolate it, that takes me away from the solution to the other side of the turning point. It gives me a new guess that x equals 1. When I evaluate that, then I get a value for y at x equals 1 of 1. When I find the gradient and extrapolate back, then my new estimate lands me back at x equals 0, which is where I begun. So I have a problem. I seem to have magically landed in a closed loop where my estimates just cycle back between x equals 0 and x equals 1. And I never get close. I never even go anywhere near to the solution at x equals minus 1.769. There's another problem, which is that if I'm close to a turning point, this bottom here, to a minima or a maxima, then because my gradient will be very small, when I divide by the gradient in the Newton-Raphson equation here, my next estimate will take me zapping off to some crazy value. And therefore it won't converge easily, it'll dive off somewhere. Those are the problems. So that's the Newton-Raphson method. We iterate to a solution to an equation by each time making a new estimate for the solution, using the gradient to extrapolate towards the solution, then going again and again and again. And most of the time, this works really well as a means to step towards the solution. So, what we've done in this video is look at a method for using just the gradient to step our way towards solving a problem. This method is called the Newton-Raphson method, and it's a really powerful way to solve an equation just by evaluating it and its gradient a few times. It's as if you're standing on a hill in the fog, and you can know your height, and you can know locally what's going on around you. You can know how steep the hill is, but you can't see the whole landscape around you. You don't know what it looks like. You don't know how to get down the mountain, if you like, down to a nice, safe place that doesn't have cliffs. So what you do is you guess based on how steep the hill is locally around you which way to go. That you want to go down to sea level, so you go down the hill. Then you take that step blindfolded, and when you get there, you ask again what height you're at and how steep it is, and then you keep making more steps down the hill until either something goes wrong and you need to go back down the other way, or you get home to where you wanted to be. The point is you don't need to know what the landscape looks like, the function. You just need an altimeter, the value of the function, and to be able to feel with your toe what the gradient is like locally around you. What we'll do in the next video is look at how to apply this where we've got multiple variables, not just x. And that will involve finding the gradient vector, how to go down a hill on a contour plot. Okay, so now we've looked at the Newton-Raphson method, which uses the gradient to iteratively solve a 1D function of x, say. Now we'll generalize that to figure out how to do something similar with a multidimensional function, a function of multiple variables, and how to use the gradient to find the maxima and minima of such a function. Later on, this will let us optimize, find the best fit for the parameters of a function that we're trying to fit. Say I've got a function like f equals x squared y here. This function looks like this. And what I've got here is a function that gets big and positive when x is big and y is positive, and it gets negative when y is negative. So if I look down the y-axis, I get a projection of a straight line. And if I spin to look down the x-axis, I get an upright parabola for y positive, and one going down for y negative. And the function is equal to 0 along both the axes. Now at the bottom here in MATLAB, I've used the surf-c function to plot contours when the function has a constant value, just like the contours of constant height on a topographical map. So the question we want to answer in this video is, how do I find the fastest or steepest way to get down this graph? Now, previously you found out what the gradient of a function is with respect to each of its axes. So you can find df dx just by differentiating the function f, treating all the other variables as constants. So in this case, we've got a function f of x, y is equal to x squared y. And so df dx is equal to differentiate that, treating y as a constant. So that's just 2x times y. And df dy is equal to, well, the x squared we treat as a constant, and y differentiates just to 1. So it's just x squared. Now, we can write down these two gradients in a vector, which we call the grad of f. So this guy we call grad. And this vector is just the vector where we write them down as the components of a vector. So we say that grad is that. It's just the vector found by writing down df by dx and df by dy in the x and y locations of the vector. And grad is like the most awesome vector ever. Grad is the little vector that combines linear algebra and calculus together. So grad's a lot of fun. So if we run along a little vector r is equal to dx 0, then if we dotted that with grad f, then we get df dx times dx plus 0. So we'd move the amount dx along the x-axis. So this is doing the right sort of thing, right? A dot product of grad f with a vector is going to take, it looks like, some amounts of df dx along the x bit of that vector and some amounts of df dy along the y bits of that vector. So it's going to tell us how much we've gone down. That's sort of how grad works. And the important thing is to remember this is evaluated at f has some values in the space, a, b. So it's evaluated at a location. So then if we want to know how much the function will change when we move along some unit vector in an arbitrary direction, so we'll call that unit vector r hat, and we'll give it components c and d. So c squared plus d squared is equal to 1. So df is going to be df dx times c plus df dy times d. So what we're doing here is we're doing grad of f dotted with r hat. And we call this thing the directional gradient. So another question we can ask is, what's the maximum value this directional gradient can take? So we've got grad f as a vector, and we're dotting it with r hat. And our question is, what's the maximum value they can take, given that r hat is a unit vector? Well, the only thing then left when we dot them together is going to be the cos theta term, because it's a, b, cos theta. And that's going to be maximised when cos theta is 1, which means theta is 0, which means r hat is parallel to grad f. So in order to find the maximum value of the directional gradient, we want an r hat that's actually the normalised version of grad. So we can write that down, we can do that calculation. So we'll have grad f dotted with the normalised version of itself, so grad f divided by its modulus. But grad f dotted with itself is just equal to the size of grad f squared. Got to divide by the size. So the maximum value the directional gradient can take is just the size of grad f, and that's therefore the steepest gradient we can possibly have. The size of the steepest gradient we can possibly have is just the size of grad f, the sum of the squares of the components of grad. So that's really fun. The other question to ask is, which way does grad point? This is less easy to see, but grad points up the direction of steepest descent, perpendicular to the contour lines. So think, if you're on a mountain and it's foggy and you can only see locally around you and you want to go down the hill, you don't walk around the contour, you go down the hill. So if the contour's like this and I'm staring down the hill is at 90 degrees to the contour line. And think about the way it's defined. Is it up or down? df dx is positive if you're going up. So actually, grad f points up the hill in the steepest way, and minus grad points down the hill the steepest way. So grad points up the direction of steepest descent. Now, if we have some data science problem where we want to minimize the difference between our data values and our model fit, then what we want to do is find the lowest point in the function. The function is kind of the badness. We want to find the best, so we want to find the point where the badness is minimized. And like Newton-Raphson, we can use the gradient to go from some trial point down towards the solution. But in Newton-Raphson, we're trying to find the 0 point. Here we don't know what the minimum value of the function is, so we don't know how far down we need to go. It's as if we're somewhere on our mountain, but we don't know the altitude of the valley. So what we do in what's called the gradient descent method is we take a series of little steps down the hill. That is, if we started at some position Sn, then our next position, Sn plus 1, is given by Sn plus some little step down the hill, and that little step is given by minus some amount times grad. And grad evaluated at the previous position Sn. On the graph, that's going to look like taking a little step, the little blue one, down the hill, and then we reevaluate, make another Sn plus 1, and make another step, and take a series of steps down the hill. If we overshoot, that's okay, because grad will just take us back to the minimum. And notice that as the gradient gets shallower, as we come towards the turning point, then the steps automatically get smaller, because grad gets smaller. So this is quite a nice method. There are lots of ways to enhance it, but that's the main idea. It's very powerful and simple. The other thing to notice is that there are multiple local minima in the landscape, then we might get stuck in one of them. And of course, which one we find depends on our starting point. We won't find the others, we'll only find one at a time. So in the general case, there are some problems, but nevertheless, this is quite a neat method. This is just following little steps down the hill. And this is probably the main way in which most numerical optimizers work that people use in the real world. So, what we've done in this video is we've introduced ourselves to grad, the gradient vector, and merged calculus and vectors together to take our first steps in vector calculus. And that's allowed us to find a method for just using the gradient to step our way towards solving a problem for multivariable cases. And that method's called gradient descent. So we found out about grad, and that led us on to sketch out a neat method for finding the minima and maxima of multivariable functions, which we call gradient descent. In this video, we'll look at what happens if we want to find the minima or maxima subject to some constraint, that we want to find the maximum somewhere along a line or something like that. And this is called the method using Lagrange multipliers. So what we did in the last video is we looked at a function like this one, f here. This function f is x times the exponential of minus x squared plus y squared, and it's one of the standard MATLAB examples. And I've plotted below it here a contour map of the values. If I now plot just the contour map, I can plot out the vectors of grad f. As we said, these vectors are perpendicular to the contour lines and they point up the steepest gradient. Now let's return to the function we were looking at last time, f equals x squared y, which is the Khan Academy standard example for this problem. Last time we plotted grad f on both the 3D version and then dropped that down onto the corresponding contour map. Actually, it's going to be easier if we now just work with the contour map itself. So here's the contour map, and what I've done is I've used the gradient function in MATLAB to just plot out the gradient perpendicular to the contours everywhere in the space. So the low sides are at negative y down here and the high sides are at positive y up here. Now what happens if I want the maximum value for this function, f equals x squared y, but constrain it to lie on a circle? Where's the highest point anywhere on that circle? Say I have a circle of radius a squared and I want to find the minimum and maxima on that path as I go around that circle. Now you can imagine that describing an equation for how x squared y varies as I go around a circular path is going to be a complete nightmare. But that's not the question we were actually asked. What we wanted to know was, what's the maximum along that circle, not what's the value everywhere on the circle. Now Lagrange was one of those French mathematicians whose name is inscribed around the Eiffel Tower, and what Lagrange noticed was that when the contours just touch the path, then you'll have found the maximal minimum point. That is, when f is a little bit smaller, it won't quite touch the path, see it here in 3D, and when it's a bit bigger, it might cross a couple of times, see here in 2D on the contours. But when the contour just touches, then we'll have found the minima and maxima of the function f as we go around the path, our circle in this case. And what Lagrange noticed was that when the contour touches the path, then the vector perpendicular to the contour is in the same direction, up to a minus sign, as the vector of the path itself that's perpendicular to the path. So if we can find grad, we can find the minimum and maximum points and solve the problem. If we can find grad perpendicular to the contour on both the path and the function, we're away. So we want to maximize the function f of x, y, which is equal to x squared y, subject to some constraint, which we're going to call the constraint equation g of x, y. And that's the equation of a circle x squared plus y squared. And it has some value, some particular value to the problem we want to solve of a squared. So what we're saying is, if we've got the function doing something like this, and it has its grad that way, and the circle has some path that's doing that, and it's got its grad that way, what we're doing is we're solving grad f is equal to lambda, some number, times grad g, where lambda is Lagrange's multiplier, or the Lagrange multiplier. And that's all we really need to do. So we just need to set up this set of equations and then solve them. So if I take grad f is equal to the grad of x squared y, well, that's equal to, if I differentiate for the df dx, I've got 2xy. And if I take df dy, the y just goes and I've got x squared. And I'm saying that that's equal to lambda times grad g, which is equal to lambda times, if I differentiate g, x squared plus y squared with respect to x, I've got 2x. And if I differentiate it with respect to y, I've got 2y. And that's giving me two equations with two unknowns. And I've got a third equation, which is the constraint equation itself that brings in the actual value of the circle I'm particularly interested in. So I've just got to solve that. So if I take the first line, I've got 2xy is equal to lambda times 2x. I cancel the two x's, and therefore I've got y is equal to lambda, straight out. If I take the second row, the y row if you like, I've got x squared is equal to lambda times 2y. But lambda is itself y, so that's equal to 2y squared. So I can say that x is equal to the square root of 2 times y. And because I've done the square root, I've got a plus minus here. And now if I take the constraint equation itself, the third one, I've got x squared plus y squared is equal to a squared, but x squared is equal to 2y squared, so that's equal to 3y squared. So then if I square root that, I can say that y is equal to a divided by the square root of 3, and again, because I've done the square root, I've got a plus minus. So those are my solutions. So I can write those out, and I've got the solutions are going to be a over the square root of 3 times, if I take y as 1, then x is root 2 times that, so root 2, 1. And I've got a over root 3 times root 2 minus 1 for y. And I've got all the possibilities, a over root 3 minus root 2 and 1. And I've got a over the square root of 3 minus root 2 and minus 1. Now, if I find the values of the function, f of x, y, as I go take all of those, so I've got to find x squared y for that. So that's a cubed over 3 root 3, because I'm cubing that bit in effect, because they're both in x and y. And I've got x squared is 2 plus y is times y is 1, so that's 2. Here I've got the same thing, but I've got what y is negative. So now I've got a cubed over 3 root 3 times minus 2. This one's y is plus, and when this squares, the minus sign is going to disappear. So this is going to give me another plus solution, 2 over 3 root 3 a cubed. And I've got here y is negative, so I'm going to get a minus here. A cubed over 3 root 3. So I've got a max, I've got a min, I've got a max, the way I've written it out, and another min. So I've got two positive solutions, and I wanted to find the maximums, so those are there, and I've got the minima as well for free. So let's look at what that looks like now on the graph. So two of our solutions are here and two here. When we switch to the 3D view, we can see that the two with positive y are maxima and the two with negative y are the minima. So that's really neat. What we've done here is we've used our understanding of gradients to find the minima or maxima subject to some constraint equation, like a straight line or a circle. And very often we will want to make it that some of the variables in a function that we want to fit are fixed in relation to each other. They have some fixed relationship, like they're around a circle. So this is a very handy thing to be able to do. It's really useful. So hopefully that was good fun. So this week we're finally going to apply all this multivariate calculus to help us fit functions to data. This is really handy. It allows us to make sense of our data, to start doing statistics testing, and to start to really apply all of this stuff we've been doing into the real world. If you have some big bundle of data, the first thing you need to do is to clean it up. There are other courses on this, but the first thing you need to do is clean it up to get it into shape to start doing the maths with. That means figuring out what the sensible thing to do is with things like partially empty data entries, zeros, those sorts of things, to figure out if you can do any dimensionality reduction by binning or grouping the data together, eliminating duplicates, garbage data, all those sorts of things. Often the easiest thing to do is to tag all of your data so that you can reorder them and put them back in where you've changed the order, then sort them and look for funny values and then figure out what to do with those, to get rid of them altogether or to replace them with something sensible. And then once you've cleaned it up, you can start graphing it. Take averages, look at standard deviations and all those sorts of things. Of course, in doing this, it really helps if you're interested in the data. You need it to be kind of like a person that you want to figure out and understand until it becomes an old friend. If over time as you collect more data and it starts to change, you want to get to the point where you're going to notice those changes, actually. So you really want to get it intimate and friendly with your data. Once you've graphed it in a sensible way, you'll often get a plot like this guy here, which is a simple XY plot of some data. This data seems to plot like a straight line. if you know something physically about the processes involved in generating the data, or if you have some hypothesis as to how the variables are related, then you can try and fit that model to the data. Alternatively, you can just try fitting something sensible based on how it looks, like a straight line to this data here, for example. Now, I can model my straight line y here as being a function of the I observations xi and a vector a of the fitting parameters. In the case of a straight line equals y equals mx plus c, then the parameters in the vector a would be the gradient m and the intercept c of the straight line. So here I've plotted the optimal straight line for this data. It happens to have a gradient of 215 gigapascals GPa and an intercept of 0.3 GPa for c. I can also find the mean of x bar, and the mean of y bar, which are at the geometric centre of mass of that data set. Now, in order to find the optimal value of m and c, let's first define a residual r, which we define as the difference between the data items, yi, and the predicted location of those on the line at y, which would be mx plus c. So r is yi minus mxi minus c. Then I can take a measure of the overall quality of the fit, being a quantity I'll call chi-squared, which is the sum of the squares of the residuals r. I do this so that I penalise both data that are above and data that are below the line. I don't want the pluses and minuses to net off against each other. Also, I really want to badly penalise data items that are a long way away from the line. And then I'm going to try and find the best chi-squared possible, the one that's lowest. I'm doing a minimisation. So now, it's worth plotting out what chi-squared is going to look like for lots of different possible values of m and c, which is what I've done on this contour plot here. In the middle at about 215 and near an intercept of 0, I find my minimum, and the further I get away from those, the worse it is. And note that in terms of chi-squared, it's slanted. There seems to be some kind of trade-off. The bigger c gets, the lower the optimum value of the gradient m, and vice versa. And if I look on this plot, that's got sort of obvious. If I make the line steeper on the original fit, then in order for it to fit well, the intercept's going to have to get smaller. Actually, I'm pivoting about the centre of mass. And also this shallow trough here in the chi-squared value is going to be really quite shallow. So this is actually going to be quite a tricky problem for a steepest descent algorithm. It's going to be easy to get down the sides, but it's going to be difficult to get down the bottom of the valley to find the actual minimum. But nevertheless, it looks like it's going to be quite an okay problem to solve. It has one easy to spot minimum, and therefore we can find it. And note that to do this with any precision, if I do it simply by doing lots of computations here, like I've done for different m's and c's, and finding the minimum that way, plotting it all out, finding the minimum on this graph. To do this, I have to do a lot of maths. In MATLAB, this contour plot took about 200,000 computations to make. So even for a simple problem like this, we really do want to find an algorithm that's going to let us get there a bit more efficiently. Now, the minimum is going to be found when the gradient of chi-squared is 0. So if we just take the grad of chi-squared with respect to the fitting parameters and set it to 0, that's going to be our solution. Now, the neat thing is that in this particular case, we can actually solve this problem explicitly. So that's what we're going to do in this video. But then we'll go on to see how to do it by linear descent, and then we'll find a better algorithm, and then we'll explore how to do this sort of problem where it's not so easy to do explicitly. So if we differentiate the first row with respect to m, then the first thing to worry about is all these sums over the data items I. But actually it turns out that we don't need to worry about these sums because we're not differentiating the xi or the yi themselves. So they'll just sit benignly in the sum. You know, mx1 plus mx2 plus mx3 is the same as if we differentiate that with respect to m, we just get x1 plus x2 plus x3. So we don't have to worry about those sums. And then it's easy, right? We differentiate a square, that drops in power by 1, and we multiply by 2. And then we take the differential of the inside of the bracket, which with respect to m is minus xi. We can then take that minus 2 outside of the sum altogether, in fact. For the second row, it's easier because the differential of the inside of the bracket with respect to c is just minus 1. So we just get the 2 down from the power and the minus sign, and so it all looks quite easy. Keeping on looking at the second row, then the sum of c times the number of data items we can take out of the sum altogether. And then we've got the sum of the yi's and the sum of m times the xi's. And if we divide that through by the number of data items, we get our result that C is going to be y bar minus m times x bar, y bar and x bar being the average. We can carry on in that way and generate an answer to m, which I'm just going to leave here. I don't think there's any point in showing all the maths to you blow by blow. It's a bit trickier to see, and I'm not going to go through actually the maths and the derivation, but you can also find estimates for the uncertainties in C and m, which I've put up here, which I'll call sigma C and sigma m. And it's very important, actually, when you're doing a fit, to get an idea of the uncertainties in those fitting parameters and to quote those in your fit. So I'm just going to leave those here in case you need to use them. So coming back to our fitted data, we can plot it out again here. Now, the amazing thing here is just how accurate this sort of fitting really is. It's really cool. You know, we've got quite noisy data, and a gradient of 215, but the uncertainty is only 9. It's about 5%. It's really amazing. Now, you should always plot your fit and visually compare it, just as a sanity check. And we can see why this is a good idea here. This is Anscombe's famous quartet. You can find the graph on Wikipedia. All these 4 data sets have the same chi-squared, means, best fit lines, and uncertainties in the fitting parameters. But they're obviously very different data. In the right-hand 2 cases, probably fitting a straight line is just the wrong thing to do. The bottom left, if you remove the flyer data point, the gradient's different, and the intercept. It's only the top left where the fit's actually doing the right thing altogether. And there's another subtlety, actually, which is if we go back and look at C, the intercept, we can see that the intercept depends on the gradient m, which is what we said earlier when we looked at our plot of chi-squared. Now, there's a way to recast the problem, which is to look at the deviations from the centre of the mass of the data at x bar instead. And then the intercept, b now, rather than c, is the location of the centre of mass in y at y bar. And then the constant term in the fit b, that constant b, doesn't depend on the gradient anymore, and neither, therefore, does its uncertainty include a term from the uncertainty in m. In fact, if I plot out the contour plot for chi-squared, when I do that, I find that it then isn't slanted. It's a nice sort of circular looking thing. Because I've removed the interaction between m and the constant term. So it's a mathematically much more reasonable, well-postulated problem. So that's the essence of regression, of how to fit a line to some data. And this is a totally, really useful life skill, almost whatever your professional job. What we'll do in the next couple of videos is look at how to do this in more complicated cases with more complicated functions and how to extend the idea of regression to those cases. The main thing really that we've defined here that's important to remember is this goodness of fit estimator, chi-squared, the sum of the squares of the deviations of the fit from the data. And chi-squared is going to be really useful to us going forward. In this video, we're going to look at how to finally learn how to fit our distribution of heights data. Then in the following exercise, you'll actually do that for yourself. And then in the next video, we'll wrap up with looking at how to do this practically in MATLAB or Python. So we're looking at how to fit a function that's arbitrarily complicated compared to the simplest case of linear regression, y equals mx plus c, that we looked at last time. Of course, there's intermediate possibilities between very complicated and the simplest possible, but this gives you the general case before we move on to look at how to do this in the computer using tools instead of writing our own. So let's say we have a function y of some variable x, and that function has parameters in it, ak, where k goes from 1 all the way up to m. So there's m of these a's. So for example, we could have x minus a1 squared plus a2. That would be an example of some function y. This function isn't linear in a1, notice. If I double a1, I don't double the function. So it's a non-linear least squares we're going to do. Now, say I want to fit the parameters ak to some data. So I've got some data observations. I've got I equals 1 to n of them, and I've got pairs of data, yi and xi. So for every x, I've got a y. And I have an associated uncertainty, sigma I. That is the more uncertain I am about the data point yi, the bigger the uncertainty sigma is going to be. So I can sketch that out, something like this, for instance, as an example of my yi's and my xi's are there. So I've got an xi, yi, and each one's got an uncertainty sigma I there. Then I'm going to define a goodness of fit parameter chi squared there, as being the sum over all the data points I of the difference between the yi and the model of xi with its parameters ak. And I'm going to divide all of those by sigma squared, and I'm going to take the squares of the differences. So what I'm doing here is I'm penalising each of these differences by an uncertainty sigma squared when I make chi squared, so that uncertain data points have a low weight in my sum of chi squared, so that they don't affect the fit too much. If we don't know what the sigmas are, we could assign them all to be 1, right? This will just drop out. But if we have an idea of the measurement uncertainties, this gives us a way to include it. And my minima for chi squared is, of course, going to be when the grad of chi squared is equal to 0. Now, in the general case, I might be able to write down an expression for grad here, but I might not be able to solve it algebraically. So instead, I'm going to look to solve grad chi squared equals 0 by steepest descent, going down the contours, simply by updating the vector of fitting parameters a. So I've got my vector a. I'm going to say that my next iteration is going to be my current iteration minus some constant times the grad of chi squared. So I'm going to go down the gradient here by an amount given by the constant, which is sort of a pull handle for how aggressive I want to be in going down the steepest descent. And that I'm going to use to make my next guess for what the fitting parameters should be. And I'm going to write them down as a vector. And I'll keep doing that until I reach this criteria, that the grad of chi squared is 0, or which means I've found the minima, or failing that until chi squared stops changing, which should be the same thing, right? Or I just give up because it's been so many iterations and I get bored and I decide that something's gone wrong. So to do this grad, I've got to differentiate chi squared. So I've got to do d chi squared by dak for each of the k's in turn. And when I do that, well, the sum has nothing to do with k, because it's to do with I, and I'm going to get a 2 down, and I'm going to get the sigma squared has nothing to do with k. When I differentiate this, I'll get the 2 down, and then I'll have the bracket itself, yi minus y of xi and the ak's. And then I'm going to get the differential of the bracket. I get a minus sign out of that, and I get dy dak. So I get dy dak. So that's going to be my differential there. The minus 2 I can just take out. So when I come to update here, if I wrap the minus 2 into the constant, I can just make that a plus, ignore the 2. So I'm then going to get a current plus this thing, the sum from I equals 1 to n, because the minus signs will go. I'll wrap the 2 into the constant, then I'll just get this, yi minus y of xi and the ak's divided by sigma squared times the differential evaluated at a current, because I don't know a next yet. So the steepest descent formula here is just going to be that a next is equal to a current plus this sum, and I've got to be able to differentiate y with respect to ak. And this is one of these formulae that look really intimidating, but really isn't when you actually try to use it. For our example here, we take this example here, if we differentiate that with respect to a1, then we'll get that dy by a1 is equal to minus 2x minus a1. I take the 2 down and I get a minus sign when I differentiate the stuff in the bracket. And when I do dy by da2, I'm just going to get 1. So it's actually really easy when we come to finally use it, but the expression looks intimidating. So that's the steepest descent formula for the case of fitting a nonlinear function, where we're trying to minimize the sum of the squares of the residuals, and this is therefore called nonlinear least squares fitting. There are lots of more complicated methods than steepest descent for solving these sorts of problems, which we'll look at a little bit next time. But first I want you to try and give this a go and code it up and see how it looks for the sandpit problem that you were doing before. So that's the simplest version of how to do a general fitting, a finding of the minimum or least value of the sum of the squares of the residuals, for a model that's nonlinear in both the functions and the fitting parameters. So it's called generalized nonlinear least squares fitting. In this video, we're going to make some final comments on the least squares regression fitting of data, and we're going to look at how we really do this in anger in the world using computational tools like MATLAB or Python or R. So you've made a gradient descent least squares minimizer and then used that to solve the sandpit problem already. There are a few comments to make before we move on. In reality, there are a huge number of solvers for nonlinear least squares problems. We can observe that if we do a Taylor series expansion of chi-squared, then the second term, the second derivative, is the Hessian, which gives us information about the curvature or the gradient of the gradient of the Jacobian. And therefore we can shoot directly for where the Jacobian is 0, just as in Newton-Raphson, using that second derivative. Now, using the Hessian would be faster than simply taking steps along a steepest descent algorithm. Effectively, we'd be using the Hessian to give us a guess as to the size of the step we should take in gradient descent. The problem is that often the Hessian isn't very stable, especially far from the minimum. So the Levenberg-Marquardt method uses steepest descent far from the minimum and then switches to using the Hessian as it gets close to the minimum, based on a criteria as to whether chi-squared is getting better or not. If it's getting better, it uses the Hessian, and if it's in trouble, it uses steepest descent. There is also the Gauss-Newton method and the BFGS method, amongst many others, that either use the Hessian directly or build up information about the Hessian over successive iterations. And depending on the convergence, then different methods may be better than others. Robust fitting is another topic you should be aware of in case you need to look it up later. If we come back to Anscombe's quartet here, we see that the bottom left data set in our problem has just that one flyer data point. A truly robust fitting method would be unbothered by such a data point. One approach to robust fitting minimises, instead of the least squares, the absolute unsquared deviations. So it doesn't weight the points that are far away from the line as strongly. And that means it fits a little bit what visually looks a bit better. Now, let's turn to look at how you do this in the real world. In MATLAB, it's easy. You simply import your data using the Import Data tab at the top of the screen, and then flick over to the Apps tab and start up Curve Fitting, the Curve Fitting app. There, you can even symbolically define your own algorithm. You have to pick a starting guess, and it will fit your function for you. Or you can use a pre-built function that already knows its Jacobians and will therefore be faster and more efficient. In Python, it's very nearly as simple. In the scientific Python SciP set of modules, the optimizer module includes a least squares curve fitting minimizer, curve fit, which is at the link below this video. Accompanying this video, we've left you one of the SciP examples for fitting some data so you can see how to use it. This is it. And it's amazing. The fitting really works very well, produces this nice graph here of this apparently noisy data with this crazy function. And the fitting only takes 3 lines, the 3 bold ones here, 2 lines to define the function and 1 line to do the fit. The rest of that code is all about plotting it and importing the data and everything else, well, generating it in this case actually. Effectively, this set of routines in SciP is the modern implementation of what's called MinPack, which was a Fortran set of routines published by Georges Moret in 1980 and described in the book Numerical Recipes. And it's absolutely astonishing how easy it is to do this stuff now. You know, when I was a student, you were reduced to reading this long, difficult textbook. Now you just effectively write 1 line in Python. Just as in Python, in the R statistical programming language, there's also a minimizer for doing nonlinear least squares fitting of models to data. So if you like R for looking at data, you can also do all this stuff just as easily in R. So what I want you to do now is write a Python code block to fit the Gaussian distribution shown here. You'll need to give it a starting guess, and we give you the input data for the height distribution in the population. This is the final height distribution data set that we've been talking about schematically all the way through these two courses. And what you'll find is that the mean height, B here, is about 178 centimetres, and the characteristic width of this distribution is about 11 centimetres. That's parameter C in the equation here. Now it's useful at this point to think about why we need to have the starting guess. If we started with a guess here for the mean of 100 centimetres, the model curve wouldn't overlap with the data at all. So when we did a little move to B, we get no change, and therefore the gradient of chi-squared with respect to the mean B would be 0. So the algorithm wouldn't know what direction to go in. We wouldn't get a sensible answer for the Jacobian or for grad, and therefore our algorithm wouldn't know where to go to find the minimum. So in doing any of this data fitting, it's vital to come up with a good means for generating a starting guess. Here it's easy, you pick the biggest value, for instance. Not coincidentally, it's also equally important to compare the fit to the data and ask if you believe the final fit. So, what we've done in this video is we've finished our little discussion of using vectors and multivariate calculus together to help us do optimizations of functions and to fit data to functions. And it's turned out in the end to be really easy computationally. We can fit functions in just a few lines of code in Python or MATLAB or R. But now, after all this work, you understand something of how those algorithms work under the hood. And that means that hopefully you'll be much better off at figuring out how to fix them when they go wrong. For instance, when the Jacobian doesn't make any sense. And also, you've got all the maths you need to access the next course in this specialisation on machine learning.